Hello everyone. Let's start it. So thank you for making it in that early, like 8:30. My name is Zhi, and after an exciting journey in the past few days in the conference, I'm happy to introduce an even more exciting workshop on robot fine and dexterous manipulation. So we have plenty of valuable and engaging content to cover, so short summary. And robotics, in particular robot learning, is getting more and more popular. This is the largest CoRL ever, much larger than last year. There are also very cool results every few months. But are we even close to solve dexterous and fine manipulation? In this workshop, I hope you can see a lot of talks and papers and discussions on many perspectives on this problem. So for example, what is definition of fine and dexterous manipulation? How fine is fine, and how to define dexterous manipulation? Is that from multi-finger hand, or is that because of the task? And what is the challenges right now? Is that in the hardware side or sensor side? And after we have all the infrastructures or hardwares and how to learn this, how to learn these skills, and can we make them more effective when we learn them? And here's a schedule which is supposed to be, like the font is supposed to be small, and if you want to know exact schedules, you can always scan the QR codes on the top right. And we will have an exciting lineup of different speakers. Even from the top title, I can already feel there will be fruitful discussions and valuable takeaways over the days. And we also have a spotlight session. So right before the poster session, each contributed paper will get a short 1.5 minutes presentations, but still longer than the CoRL spotlight. And thank you for submitting the work and submitting the presentation materials on time, even this morning. But I also want to acknowledge the organization team who worked very hard on writing proposals, arranging schedules, writing reviews, and many hard work to make this workshop happen. And finally, the workshop is sponsored by DexMate. It's a US startup company working on dexterous manipulation. Without further ado, I'll introduce the first speaker, Oliver Brock. Oliver is a professor in TU Berlin, and today, today he will talk about dexterous manipulation, why learn it if you can just do it. Here's the mic.
Yeah, 1 second. There's no free cut. I think something strange is going on, and all of you are right in the middle of it. We've seen it all over the place at CoRL over the last days. Everybody's talking about generality, but nobody offers really a definition of what that is. And everybody's assuming, even though we don't know what it is, that machine learning, in particular deep learning and LLMs and so on, are the right approach to it. In this presentation, and I've changed the title, I would like to take a step back and look at different approaches and compare them to see maybe what achieves generality. Another thing that I was struck with is that we keep looking at videos to assess generality. So here you see, this is unfortunately, can we turn off the light maybe? There's two videos here kind of performing the same manipulation task. And my point is, even if you saw the videos, it's difficult to tell which one is more general. Anyway, I mean, it's okay. The one on the left is somewhat detectable, but I think maybe it makes sense to figure this out also for other presentations. Okay, so if we want to achieve generality, what are the options that we have? And I want to bring up very briefly at least two, right? One is kind of fitting to a function. This is from data. This is what I think most people here are propagating. And the idea would be that you need to make sure that you get the right data. The space that you're trying to cover with a function, because you're achieving generality, is very large. And so you need to make sure you find the right data to do that. That's difficult, right? Another one, old-fashioned maybe, is to build some building blocks from which you can then assemble all kinds of things. The idea here is that you have primitive operators that span the space that you're trying to capture. So these are two different approaches. There are probably more, but I think we need to have kind of a dialogue about which one of these is better and how do they work. Maybe they converge to the same thing, but we should do that. And I think we need to realize that since the beginning of AI and robotics, people have tried to achieve generality. It's not like this is something new for mobile, in the context of deep learning, right? The very first proposal that was written by John McCarthy for the Dartmouth workshop already talked about generality. In 1956, this happened, right? And in 1958, people talked about a general problem solver. So generality has been on the docket for always. So this is not new, right? This is not something that is specific to the machine learning community. I propose very, very coarsely that to assess the generality of something, we should take quotient of the degree of generality achieved divided by the cost of generality. Basically, what do we have to pay to do that? And I want to take two examples, one from dexterous manipulation and one from fine manipulation, to assess this. So here you see a dexterous manipulation. It's an in-hand cube rotation, as has become kind of the standard approach in dexterous manipulation. And you see that the whole hand, the wrist, is moving to demonstrate that you're general against gravitational forces, right? It doesn't matter where gravity is. This is open loop, right? There's no sensing happening. And as you can see, it's very robust. Just to show you one more approach to generalization, this is against gravity, but here you see generalization against object size. And note that we have now a hand with a second thumb. So this hand has 6 fingers, among them 2 thumbs. And you can see that basically up to 100% of increase in object size, the same open loop strategy successfully manipulates this thing. So I want to quickly talk about what is the building block that is underlying this. And the key, and the, wow.
Not gonna get better.
And the key is the compliance in the hand, right? This is the first building block that achieves generality. The compliant hand can absorb energy and can give it back to the manipulated object. And if you program the hand, the physical hand, by changing the configuration, you can make sure that this restoration of energy into the object happens in such a way that it self-stabilizes the manipulation action. So this is basically what imposes a very coarse grid over the entire space. This is, I think, the key to solving manipulation. Right? The robustness is built into the hand. So this is the first conceptual thing that we have. It's a funnel. It basically self-stabilizes under a variety of circumstances. And there's lots of papers that we've published demonstrating this with experimental data. The next level of abstraction that introduces generality are position spaces, right? You can grasp something like this with the index finger and thumb, or you can grasp it with 4 fingers and the thumb opposing. It's basically the same grasp, right? So by putting all of these things together, abstracting from the physical instantiation of the hand, we achieve another level of generality. Then we take these blue funnels, these summarized opposition space funnels, and we compose them in such a way that they are robust to the expected failure modes, and we call that then the green funnel. And these green funnels now are so robust that it's simple to compose them, right? We have now reached a level of robustness that we just need to compose them, and we can hopefully span the space of all possible manipulation actions, right? And if we manage to achieve that, then I would say manipulation is solved, right? If we manage to achieve that. But this is just one approach, right? This is one approach. And the videos that you saw were produced by Alexander and by Agrawal, but it's just one approach. There are many other approaches to achieving similar skills. These are just a few. And in order to compare generality and which one, is it the function learning or is it the building block approach, is the better one, I want to look at the one that I actually think is the best. So I'm not trying to pick on things, right? I think this is the best one that we've seen so far. This is called AnyRotate, and it's from Nathan's lab in Bristol. So in order, let's look at the point of what's the cost of generality. In order to do this, they need a customized hand and a sensor configuration. You can see how the sensors on the two external fingers are rotated by 90%, 90 degrees, right? So it's customized. There's tactile sensing in each fingertip. It uses closed loop control, you need to train, and you limit it because you need the data. So we can get away with removing all of these assumptions, right? So the cost of generality in our case is much, much lower, right? We don't even have sensing at all. And obviously if you don't need sensing, but you achieve the same skill, you're much more general, right? So I could go now and dive into details of performance metrics and which one is more general, right? But that will be discussing here the degree of generality, but I don't want to do that. I think it's sufficient to point out that the cost of generality that we have to pay in the building block approach is much, much less compared to what you have to pay with all the approaches that we've seen in the functional approximation approach, right? So I'm looking forward to your questions about this, but if this is true, then why should we try to solve manipulation with the function approximation approach, right? I think the toolbox is a good idea. Okay, let me give you another example. Here is what I would call a fine manipulation problem. Here are a bunch of rocks, and you try to learn from demonstration. This is a fine manipulation task because it's actually super tight clearances. Even humans get stuck using this, right? It looks super simple because we do it all the time, but it actually is a complicated task. So you want to learn on one lock and generalize to all the others. There's another set of locks with chains, and you want to generalize to others, or you want to generalize, across opening different kinds of drawers. Here you see a video of a demonstration executed on one particular lock, right? And it's very unsurprising that the student, whose name is Ching, can do this. Then we have a phase that's called augmentation, where the initial demonstration is taken and the robot goes in and says, I need some more information. I know that that demonstration was not complete. I need to get some more information. So this is all the augmentation phase here. But once this augmentation is completed, and you're seeing it, sped up by factor 3 or 5, but it's basically seconds that it takes. The policy that we extracted from the single demonstration generalizes wildly, right? Because actually none of these distractors matter to the policy. The policy really only is concerned with what is important for executing it successfully. So you can see different blocks, right, that are being used. The positioning is changed. This is a much bigger lock now, and so on, right? I mean, you get the idea, right? This single demonstration generalizes. So we can again explain what are the building blocks here that generate this generality. Number one is we extract from the demonstration a sequencing of different contact-based controllers. These contact-based controllers, we call them environmental constraints, right? Because they exploit the environmental constraints. Look like this, and you can see that this is kind of shaded out because from one demonstration you cannot get ever the whole picture. So the augmentation phase doesn't need to augment the sequencing, but it augments the funnels, our controllers, to get more information. That's why it was kind of playing around with it. And then again, we can compose. This is not needed for the things that I'm showing you, but we have also a method to include human corrections when the robot does something wrong. Okay, so far so good. This is published work, minus the human corrections. But then out came Furniture Bench. I don't know if you've heard about it. It's a benchmark for long horizon manipulation tasks. And my student said, that's strange, because that benchmark is super easy. And so in his, he took his approach and in an afternoon solved this, problems from this long horizon complex manipulation benchmark, which is called Furniture Bench. And here you see, I won't have time to play the whole video, but here you see, it's a 9-minute video sped up at different places, but you see here the demonstration, and it's again, from a single demonstration, it's solving this problem, right? From a single demonstration. All the other approaches that solve furniture, or that try to solve Furniture Bench, have hundreds or thousands of demonstrations and get success rates maybe of 40%. This one gets 90%, and I'll show you the failure case in a second. So I think by now we're at the augmentation phase, right? Where it's trying to gather additional visual and haptic data to complete its policy. And I'm going to start jumping around because the video is too long. Let me jump to, and then, it does an augmentation, and then it starts executing. I'll jump to the beginning. Oh no. I can't jump around. I can't. So, well, I think I just missed it. But the failure case, in any case, happens because the robot collides with something in the environment and therefore doesn't get the right grasping position. So we count that as a failure, but it could easily be fixed simply by including obstacle avoidance, right? And then, this is, I think, you see that there's 10 executions. The executions vary. We remove this plate. You see now that there's a tilt. We can put this plate in any position and configuration. We can put which is something that all the other approaches cannot do. They require exact object positions. So this generalizes much, much more than all the other approaches. The success rate is at least twice as high as all the other approaches. And let's look at the cost. Right, so we have one demonstration, right? And I really need to emphasize this. It's a single demonstration against hundreds versus thousands, right? Or thousands. It's a 5-minute computation to extract the policy from the demonstration versus, computing lots of things on simulation. Success rate is 90% versus much less in all kinds of other approaches. Generalization, it transfers between many instances and tasks. And it wasn't even designed for this, right? We developed this for a different kind of task, and it just transferred to this new benchmark. So this is very low cost and very high degree of generality. And again, it's based on clever choosing of building blocks. So I think, these are strong arguments in favor of building blocks. Here are the people that did this work. No, that's just a joke. It's not a deep learning paper, so it's just this guy who did it. Right? So, coming back to the beginning, the question is, what's the right path to generality? Right? I've only kind of opened up 2 possible paths, and I think there might be completely different ones, there might be sub-paths, but the most important point I want to make is we need to have a discussion about this, right? We shouldn't just assume that we know the answer to a problem that we haven't defined yet. And I think that what I've shown you is making the point that it's worth having this discussion because we might be barking up the wrong tree, right? So I think we need to have a discussion about what are the right approaches to achieve generality in which kind of problem, right? And so I hope that the 2 things I showed you, you're surprised that an old school approach actually seems to be, at least today, beating the modern, large simulations, much data, and so on, high computation approaches. So that's something I'm looking forward for you to ask questions about. Thanks. And obviously, the answers, both of these need to be used together, right? But yeah.
Yeah, you mentioned that it knows what things to pay attention to. How does it know that? Or what is it? How does it know what to pay attention to?
Well, when you say it, I'm not sure when I mentioned that. So
When you were talking about the augmentation,
yes,
after the first demonstration, you mentioned that the policy or what the mechanism that you're training knows what things to pay attention to and what to ignore. That seems like the critical part, but I missed how it knows that.
So the visual information is only used for visual servo, right? Because once you're holding on to the thing, we're switching entirely into force space, and we're performing the actions in a force space. Now, the visual augmentation happens because the robot knows where it grasps something, right? It has proprioception, it has forward kinematics, and so it knows this is the region in which I grasp something. And then it looks at that region from many perspectives, saying, okay, next time I will see this, that's what it might look like, I need to then grasp that.
Got it, thank you.
Any other questions?
Come on, I want an attack. Yeah,
No
Dieter.
attack, of course.
No, please, please.
No, but yeah, just wondered. So there's the other kind of generalization where you would want to actually learn to be able to do these without requiring even a single demonstration anymore in the future, right? Where you kind of train, let's say, on thousands of these kind of settings, and then train perception modules and policies and things like that that actually generalize to totally new assemblies and things like that. And I'm wondering, do you see that this approach will simply be able to do that?
No.
And then also related to this, there seem to be some assumptions hidden in this work about, like, okay, you can solve the task, for example, by some kind of key point detections and things like that. Can you talk about that a little bit? Especially on the visual perception side, right, where I think that's at least something where learning clearly plays a role, right?
Yeah. Okay. So the first question you asked is, and this was discussed yesterday during the panel, right? That if once we have acquired a set of basic skills, then we might be able to start composing them in order to achieve that generality from zero examples, right? So I would say this is a way of learning a super robust basic skill, and then the idea would be that once you have these green funnels, these robust skills, that sequencing them is very simple, good old-fashioned AI, right? So that's then how you achieve this zero-shot generality, by having extremely robust primitives that you can sequence, right? So that's the first. The second one, yes, it's true, we need visual features, but I think there's no way around that, right? You need to be able to detect an object. So we actually tried all kinds of off-the-shelf deep learning approaches for feature detection or for object localization, and none of them worked, right? This was white plastic on top of a white table, and even though deep learning is super amazing and has in particular computer vision really changed the game, we could not make this work. So, but if you can make that work, you can simply plug that in here, and it works.
Just to follow up with respect to these, you said these super robust skills, but even if I think about the trivial skill of, let's say, threading a nut on a bolt or threading an object or inserting something, in the very broad general setting, these individual skills are still actually very, very difficult to be able to make them robust. Do you think your setup just can solve all of these in the wild?
I don't know. And I mean, the threading in the nut, that's what's happening when it was assembling the table leg into the flipped over table, right? I mean, that was putting in a screw, basically. But it's a simple, large clearance, 3D printed thing, right? So I don't want to make a claim that this, do I want to know? Let me not make that claim that, this approach can solve these other things, like a real mechanical nut in a car or whatever, right?
Yeah.
And that was just, also not my point, right? I wasn't trying to push these two approaches to say, hey, we've solved everything, right? I think that would be an exaggeration to say the least. I was saying it to say, look, there are various ways of doing things. We need to understand what is the benefit of the method and what's the cost of the method, and we need to compare it. And right now, I think the method that everybody is banking on a benchmark created by deep learning people, is losing. And I find that surprising, and this would be the community to have this discussion, right? And I didn't see that discussion over the last 3 days. So that's why I gave this talk.
Yeah. No, that's a great point. I agree.
Okay, let's thank the speaker again. Yeah, I think we can have the next speaker step in. Our next speaker will be Stephane from ISIR, and he will talk about learning to grasp from dataset generation to application on real robots. There is the mic.
Okay, do you hear me? So I will take the different stance than what was said before, although I fully agree that this is a very interesting point of view. And the question I will consider here is to get data, to avoid to get demonstrations, by the way, by using learning algorithms. So if we want to make fine manipulations and dexterous manipulation, one of the issues we have at the beginning, if we do not have a nice and clever, is that okay? Yeah. Manipulators is to find a way to grasp it appropriately. So if we want to use learning approaches to do that, we are facing an issue, which is that this is basically a binary task. I mean, we either succeed or fail, which means that for reinforcement learning algorithm, it creates issues because we first have to discover solutions by chance. We have to test many things and hope that we'll discover a success at some point before being able to optimize the reward and make it solve it and repeatedly and efficiently. So we've tried to look at the chances to actually get a policy that will grasp an object. So we made experiments on the cooker arm in simulation with a two-finger gripper or with an Agrawal hand, and we looked at the probability to get something out of just random movements. So we have a random trajectory, and we're just observing in the end if we're able to catch different kinds of objects. So we're able to touch them from 10 to 50%, so that's not really a surprise. But if we look at the success rate, then it's quite low. I mean, we need more than 10,000 attempts to get a successful grasp, which is not surprising because if we not put constraint, the chance that we grasp an object, I mean, in the whole trajectory space is relatively low. So then it creates an issue for learning because that part is really a problem. So how to solve it? There are different approaches. We can try to make reward shaping, but for grasping this is quite tricky. We can use demonstration, as was very nicely shown before. But if we don't want to use demonstrations, then the basic idea is to somewhat constrain the problem to increase the probability to get a solution. And so in this very impressive work, by Sergey Levin's team. They have succeeded in learning in the real world, but they have set the problem so that the success rate for just random movements is in between 10 to 30%, so 1,000 times more frequent than what we have observed in our case. Okay, so the question is, are there other alternatives? Can we discover grasping movement for any kind of grasping, so not just two-finger grip grasping, and so also with dexterous hands on any objects on any robot hand. So if we want to do that, we have to improve the exploration ability of our algorithm. So this is where we can propose something. So this is the basic scheme of direct policy search approaches. So you want to learn through a reward function, you want to maximize the reward function, and what you want to get in the end is the set of parameters of your policy that will maximize your fitness function. So we can proceed differently, and this is what we have done in an approach called quality diversity. And in that case, when we evaluate the policy parameter, we get a reward function, a cumulative reward. We also call it fitness. We get a behavior also. So behavior is used to compare different policy. And so the idea is not to say that one behavior is better than another, which is the goal of the fitness. It's just to say that this is different. Okay? It will help us to explore. And what we want to get in the end in our algorithm is not just a single set of parameters that will optimize our fitness function, but a large set of points. And this set of points needs to be as large as possible so that we can cover the reachable space. So we want to find all the possible behaviors that are within reach for the policy we described, for the robots we have considered, and for the experimental setup we have. So we want to have at least one policy parameter that is as close as possible to any behavior we may select. And among those, we also want the policy that will maximize locally our fitness. And this point is very interesting because most of the time, the kind of reward we want to put are reward that will say, okay, I don't want to collide with obstacles. I don't want to consume too much energy. I want to be stable. But the easiest thing to maximize that reward is just not to move at all. Okay? So if you want to use that kind of approaches with this context, you need to find clever ways to combine it with a fitness, with a reward that pushes you towards doing something. But in that case, you don't need to do that because you will just compare the policies that have similar behaviors. Okay, like I will grasp my object in a particular way, and among those that grasp in this particular way, I want those that minimize energy consumption, that are more stable, etc., etc. Okay. So if you want information about that, there's a website in which you have a lot of resources about this, algorithms, tutorials, papers, and libraries that to make some experiments. So let's come back to grasping. So we have used this approach to learn how to grasp with an algorithm called Mapedit that is very basic, just a few lines of code, not a lot of parameters to tune, which is quite nice. And the basic idea is that you sample solutions, you evaluate them to get the fitnesses, to get the behavior descriptors, and then you put them in a grid that corresponds to your behavioral space that is discretized. And it's very basic. If you happen to be in a cell that is empty, then you just have the solution. If it's already filled, you compare the fitness to keep only the best one. And that's it. That's very, very simple. But if you do that, then if you use a fitness function that takes into account the energy consumption, the grasp stability, or zero if you do not grasp, then you can get something that is very diverse in terms of grasping movements. We learn in simulation, so if you want to transfer to real robots, you need to be careful, and so we use domain randomization and put some variability on object poses, joint states, friction coefficients, and in the end we have a transfer ratio from simulation to reality that is around 84%, which is quite good for something learned in simulation. So, what does it give on real robots? Well, we have tested it on many different platforms. on Baxter, on your arm, on the Franca arm, and with different grippers, with two-finger grippers, with Baxter, with the Baxter gripper, with an Allegro hand, with a shank hand, and we can generate hundreds and even thousands of grasping movements with that. Okay, so in all of those examples, all the movements you see here are just open loop movements, which means that in simulation, we put the object at the right place, and then we learn to, we explore to find trajectories that will grasp the object when it is here. So of course, when we want to apply it to the real world, it's not very useful, so we need to adapt it to the position of real objects, and we can do it with a vision pipeline. We detect the position of objects, we get the 6 degrees of freedom pose of the objects, and then we can just adapt the trajectory so that it grasps the object at the real position, so not only the position it was in simulation. So okay, so that's a first step. But now we want to go further. I mean, what would be great would be to have huge data sets. So we are clearly here in the mainstream approach of getting a lot of data, which can be debatable, and I can certainly understand that. So we can use these approaches to generate a huge data sets to train approaches to find out how to make it more efficient and generalized to different positions, generalized to different kinds of objects, etc. Because here we need to know the object's shape. So we have added some priors to accelerate the sampling, like classical priors that are used in the grasping literature, approach-based prior, antipodal-based priors for all the grippers that allow to do this, so basically two-finger grippers. We don't have it for dexterous hand manipulations. We sample directly in the grasp space, so in the position of the gripper, instead of having the full trajectory, as I presented before. And when we do that, with those approaches, we can be quite efficient. So you see here the sampling efficiency. So for the 100,000 samples that we have generated, a bit more than 60% of them generated efficient grasp. So we are quite high with respect to the kind of success ratio that I have presented before. So if we compare to our approaches, like the one used to generate the NVIDIA acronym datasets, we are more than 2 times more efficient with this approach, and we can easily test it on many different grippers with almost no adaptation. So the one thing that I can say that for those dexterous hands, we rely on synergies. So we define different ways of moving the fingers, and we explore to discover the position of the hand before closing, and we close with different configuration of the fingers, and this is what is also explored by the algorithm. So we have quite high success rates, and that allows us to generate a lot of examples for many different grippers. So we see here the Franca arm, Barrett hands, an Allegro hand, the shadow hands. And what we have done recently is that we've tried to push it a bit further. So with the Franca gripper, we have considered a huge data set of objects. So we have 40,000 objects. And so coming from different data sets, YCB, ShapeNet, KIT, GraspNet, EGAD, 3DNet, and we have tried to generate the largest set of grasp poses, and we end up with 60 million grasp poses, so much larger than the acronym dataset. And we can do the same basically for any kind of gripper, as we just have to relaunch the algorithm. So you have here the set of different objects and all the different grasp poses that have been generated. which is quite large. But it has a huge cost. That's clearly an issue in terms of computational costs. Okay, so this is the end. So if you have any questions, so this is the team of the people that have contributed to that, and the projects in which it has been done. Here Robin or PR Robot, that are both European projects. So thank you for your attention, and if you have any questions.
Okay, I think we have time for questions. Yeah.
So it's collected independently for each hand, or is there? Do you get benefit from studying this hand when you start using this hand, or is it kind of independent for each hand?
So here, for the moment, it is independent, but we have tested some transfer learning approaches in which we bootstrap the learning on an object or on a different hand with data set that have been generated on a different, and it somewhat helps. But I mean, as the hand may be quite different, I mean, the grasping is not easy to transfer. I mean, if your hand is too different.
Okay, any other questions?
Hello. I want to ask, how is the grasping stability evaluated?
We are just checking if the object is stable at the end. We are moving a bit the end. That's very simple. That's very basic. We are just checking if the object is tightly linked to the end effector. If it's not moving while we are moving the end effector.
Okay.
Thanks for the great talk. I was wondering that so for now we have like a lot of different grasp and sampling strategy, and you mentioned that we have some wire-based sampling based on antipodal and like approaching vector. But now we also have general purpose simulator like all this ISAC stuff, Majoko, Pybolis. So and actually this analytical method and the simulation-based sampling method are quite aligned. They both based on some human rules. To generate the feasible grasp path. So how do you like, what is the attitude towards this kind of to grasp sampling strategy using general purpose simulator or some like antipodal based solution?
Yeah, so here, all the things we have done rely on that kind of simulations. We use Pybolet simulations, and the reason why actually it works, if you look at that, it works quite well even if we don't use those antipodal strategies, I mean, to reduce the sampling strategies. So it works, it's just that if we are roboticists and if we know, if we have some knowledge about how things work, we can make it faster. That's it. But if we don't, I mean, we can use those approaches and it will already generate interesting results. And actually, if we have, in some grippers, I mean, we do not have those strategies. We do not know. I mean, if you come up with a new kind of gripper, you may not have the physical relations that can guide your sampling strategy. So in that case, you will have to explore more widely. But if you have the knowledge about that, you can include it.
You're exploring it in sim or
in simulation. We explore only in simulation. But then, what we do in simulation is to use some domain randomization so that the transfer to reality is okay. But then the drawback is that we need to have the 3D model of the gripper and of the objects when we generate. But the idea is that with such large data sets, then we can learn strategies that we not rely on the object, I mean, whatever, GraspNet, DexNet, or that kind of approaches that do not need to know the object's shape.
Okay, let's thank the speaker again. And we have a little bit schedule change, and our next speaker will be João. João is a researcher in German Aerospace Center, and today he will talk about adaptive learning and assistance for real-world robot manipulation. Using Type C.
Can avoid it actually.
Hello? Okay. Okay, so good morning, everybody. Thanks for being here today. My name is João Silvério. I'm with the German Aerospace Center, DLR. And today I'm going to be talking about adaptive learning and assistance for real-world robotic manipulation. So, I feel that my talk is placed a little bit in between the two previous talks, which is something I'm actually quite pleased about. And today I will argue that in order to learn Dexterous real-world manipulation robotics, there are three key components which are quite important. So the first one is the ability to handle uncertainty in perception, especially in combination, especially in insertion tasks, in highly precise insertion tasks, and particularly when the robot needs to take into account different policies potentially acting on the robot. So for example, visual serving policies and other policies that generally control the robot arm, for example, to move towards different insertion zones. The other component is related to handling object variability. So, especially nowadays, we have more and more cases where the object shape changes, especially during manipulation. And I argue that we need to be able to adapt to different objects in this context, especially online, adapt online to the object changes. And finally, we need to be able to ensure safety when learning autonomously. So in many situations, it's difficult to have these two first cases, and the robot needs to learn autonomously by itself, and we need to have safety and both efficiency. And so my key arguments today is that for the first two situations, having appropriate uncertainty modifications that allow us to seamlessly, let's say, fuse and combine existing policies in principled and seamless ways can take us a long way. And for the latter situation, I argue that domain knowledge, especially encoded in terms of constraints, can help ensure these two aspects. Now I'll start with the first topic. So at DLR, we are highly involved in high precision assembly in space in the context of the ACOR project. And here we have a situation of, I would say, a classical teleoperation scenario with an operator. So this is a bilateral teleoperation scenario, so there's haptic feedback in both ways. So we have a teleoperator and a remote setup where the robot has an end effector mounted camera, and it needs to perform these highly precise PCB board insertions. Now the interesting thing here is that I argue that we need two types of assistance. In other words, a multimodal assistance framework to succeed at this task. So the first type of assistance is trajectory guidance, and the second one is visual guidance. So in the first case, the assistant is aimed at keeping the robot in relevant task space regions, whereas the second one is aimed at guiding the user towards targets. So as different target connectors appear in the field of view, the robot is guided towards the different targets. And this means that we need to be able to handle appearance and disappearance of different, let's say, target connectors, or more generically, targets in visual circuit. So for this, we propose an approach based on adaptive visual serving features. And we formulate this as treating each candidate target as a candidate feature. So we have M generic candidate features, which can change throughout the manipulation. And we model each feature in a probabilistic manner by assuming that the pose of each feature is Gaussian distributed, is conditional on the end effector pose, so it changes as the end effector moves around in the workspace. So this is parameterized by mean and the covariance matrix, and we use this representation in a mixture of experts formulation to design assistance. Particularly, we treat each feature as an expert in our mixture of experts model, and we use as gating function an RDF kernel that basically measures the distance between the target connectors and the current end effector pose. We approximate this distribution by its first two moments, mean and covariance, resulting in a single Gaussian, and we use this to regulate the stiffness and assist the operator. So when the user is far from the board, the uncertainty increases and the stiffness is lower, and when the user gets closer to each of the connectors, the Gaussian, so the covariance decreases and the assistance increases. So this is a way we have developed to provide assistance based on the detections. Now for the trajectory part, one popular way to design these trajectory features is by using Gaussian mixture models, such that users can essentially demonstrate what is the trajectory guidance that is required for a given task, Now the interesting thing is that Gaussian mixture models are also a mixture of experts. So we have, in this framework, we have a mixture of experts both for visual guidance and for trajectory guidance, which makes it very well suited for productive features, where we try to extract the key features of each type of guidance through productive distributions. And here you see how the uncertainties coming from the trajectory and the visual serving guidance are merged into a single policy. So together, this results in behavior like we see here. So at the beginning, the visual uncertainty is high, so the pink covariance is quite large. And you see that the red covariance matches more the trajectory guidance feature. So at this point, the robot is focusing on the trajectory guidance. As the robot approaches the target connector, the visual guidance takes over, and the user is able to insert in a given connector, but also to switch between connectors as required. Now, this was about the first situation where objects are somewhat rigid and easy to model. And now we'll look into, for the second part of my talk, we'll look into how to handle object variability, especially online. And here we're motivated by manipulation of deformable objects, especially food items. And here we argue that we need different manipulation strategies depending on the object configuration, as we see on the left. And our aim is to adapt manipulation strategies to new object configurations. So we treat this problem as learning of a policy from object configuration and from both object configuration C and robot state X to an action. And to be efficient learning-wise, we want to do this from demonstration. The problem is that we need to be wary of distribution shifts, and we need to have some guarantees that we converge to the goal of the demonstrations, right? So to address this problem, we formulate the problem of learning this function using kernelized movement primitives, which are a motion primitive, a kernel-based motion primitive formulation that encodes both epistemic and aleatoric uncertainties. And particularly, we use this by treating the problem as setting the input as both configuration and robot state, as I wrote here above, and using the KNP to encode the action from the demonstrations. And since the KNP combines both epistemic and aleatoric uncertainties, we're able to compute them separately. And what we propose is to rely on the epistemic uncertainty to design additional policies in a way that these goals are facilitated. So again, we come back to the concept of composing and fusing different policies. Particularly in this approach, we consider three different policies at the same time. A learning demonstration policy that is both state and context dependent, learning the control actions. It is essentially the output of the KNP. However, this has the undesired behavior far from trajectories where the robot behavior can be potentially unpredictable, right? To counteract this, we formulate what we call a stabilizing policy, which is an epistemic uncertainty dependent policy that guides the robot back to the demonstrated trajectories. And for this, we use directly the epistemic uncertainty of the KNP prediction. And third, we use a goal attractor policy, which is simply a linear state feedback policy that ensures convergence to the target poses of the demonstrations. And together, we formulate these policies as the combination of these policies, again, as a mixture of experts with dynamic weights, where the weights are depending on where the robot is in the state space, activating each of the different policies depending on the epistemic uncertainty. So we have evaluated this approach in two different scenarios, two different manipulation and grasping scenarios. So on the left, you see a scenario where we consider as context the grasp state. So it's a binary variable 0 and 1. And here, the demonstration consists simply of grasping this cylinder. In the second case, we have the context being the object configuration, described by 2 points C1 and C2 directly on the object. And you'll see in the next video more details about this. So, provided one demonstration of each grasping and lifting of the cylinder in the first scenario. And what we see is with our model, the robot is able to essentially switch between learned vector fields based on the detected grasp state. So here, the cylinder is being pulled down by a cable with a force that causes the cylinder to slip off the fingers at the beginning of the task. But then at some point, we release the cable below the table, and the robot converges to the vector field that ensures that the cylinder is lifted upwards. So in this second scenario, we have the context being described by the object configuration. Again, it's the formal object, and we see that as the manipulation, as the configuration in the hand of the object in the hand changes, the manipulation strategy, so the strategy that the robot follows to place this fish fillet on the tray changes, and we see this as changes in the vector field that the robot is using to generate its end effector velocities. Okay. All right. So these first two scenarios were scenarios where we could either teach the tasks from demonstrations, or we could model much of the things we wanted to take into account. However, there are scenarios where this is harder, especially scenarios that require contacts, where the tasks require contacts with the environment. And for this reason, we turn to autonomous learning approaches like reinforcement learning. And what I argue here is that with domain knowledge, by using domain knowledge, especially in the form of constraints, we're able to do this type of learning in a much more efficient way. So for this, we propose to guide reinforcement learning using shared control formulations. And here we leverage a shared control formulation developed at DLR, the so-called shared control templates, which are pretty much a classical shared control formulation in the sense that they rely on a human input from an external device to control the robot, but they define two key components. The first one are input mappings, and the input mappings essentially define mappings from the input device degrees of freedom to the Cartesian degrees of freedom of the robot, which can be non-trivial, as well as active constraints, which are used to keep the robot within the required regions in the task space. Now, what we propose in this case is to replace the human by an RL agent that will learn different tasks on the real robots while enforcing these different constraints and input mappings. And the key idea here is that by working under this framework, learning is potentially safer because constraints are enforced during learning. Learning is also faster because the constraints, in principle, do not need to be learned. And this both simplifies the reward function design as well as facilitates direct learning on the real robot. So as I said, this approach facilitates reward function design. So particularly, it allows us to more easily split rewards into primary and secondary rewards, where the primary rewards are focused on task completion and task progress. So here, this D variable is a variable that comes out of the SCTs that indicates task progress. So as D decreases, the robot progresses across the different phases of the task. In the secondary reward, we're able to focus more on the execution quality by trying to minimize aspects like energy consumption, contact forces, jerk, and so on. So this allows us to write rewards in a bit more principled way. This is what a reward would like for a task where we want to encourage completion, but also minimization of control efforts and contacts with the environment. So we have evaluated this first in a task, in a pouring task, a task without contacts. Sorry. And here we have observed that by guiding the exploration with SCTs, we're able to learn the task in about 65 episodes. So we're able to achieve a success rate of 100% in just 65 episodes in the real world. And interestingly, because the constraints are defined a priori and are enforced throughout the exploration, there is no spilling throughout the learning. And this using a rather simple or a rather straightforward reward function. And then we focus on tasks with contact. So here we have this task in the lab that consists of inserting these grid clamps in the holes on the table. It's a task that is difficult to demonstrate because the optimal force profiles are difficult to capture in the demonstrations. And here we turn to reinforcement learning using this framework. So we encourage progress to the D primary in the SCTs. and we encourage also minimization of interaction forces. And so in this case, the robot is able to learn the skill with optimal forces in about I think 70 episodes in the real world on average, and interestingly, is able to learn it with say optimal force behaviors compared to a baseline that doesn't use this force cost in the real world. So this brings my talk to an end. My take-home message would be that learning Dexterous manipulation benefits from both uncertainty modifications and prior knowledge. And certainly where awareness facilitates multimodal manipulation and contributes to handling distribution shift. And prior knowledge from shared control formulations particularly, especially at the level of input mappings and constraints, can improve autonomous learning through RL in the real world. So I would like to thank my group at DLR for their contributions. I'd like to thank you for your attention, and I'm happy to take questions.
Okay, we have time for several questions.
Thank you for the talk. So I have one question on the different vector fields that you were combining. I guess that the strategy you use will depend on the environment. I mean, sometimes you can go straight to the solution, or you need to exactly follow the path. And I did not get how you manage to find the right strategy. I mean, and to adapt the parameters of the different.
Yeah. So here it's the epistemic uncertainty that you compute by computing so it's still a function approximator, right? So you use the C parameter gives you the shape of the object, and this is the parameter that basically parameterizes your vector field. So for a certain C you go one way, for another C you go another way. This you get from currently we get it from the camera basically, from the simplified object parameterization.
Thanks for the brief. For your second work, you mentioned something about the configuration for objects. How do you define them? Is there a better way of making it more general to different objects?
Yeah, so we're looking into that. So the focus here was to explore the role of the epistemic uncertainty into keeping us close to demonstrations. So we kept the configuration, so the representation of configuration rather simple, but especially after this CoRL, I think that there can be ways to have more generic representations, especially across categories. So you can have different types of objects using the same type of representation, and we're using policies that are trained for some objects on other objects. But this is an active topic in the group, I would say.
Any other questions?
Yeah, one question about the DS. When you add the three DS together, how do you determine the weights of them? And is there any global stability guarantee or not?
So, global stability is not guaranteed in a hard way, but rather in a soft way. So basically, at the end of the skill, at the end of the vector field, based on the activation from the epistemic uncertainty, you can guarantee that the goal attractor is activated, and the task will finish there. But it depends on the kernel you choose, depends on the kernel parameters. So for certain kernel parameters, you can have guarantees, but they're not hard guarantees. Let's say.
And also for the weights, how do you determine the weights for the three DS?
So they have to they sum to 1.
Yes.
And the one from the epistemic uncertainty, so the one from the stabilizing policy depends on the epistemic uncertainty, and the other two are derived from this one. I can explain both one.
Thanks for the interesting talk. Concerning the last work, so you use these shared control templates as an action abstraction. Was it something you chose specifically for the task you were looking at, or because there's a lot of different action abstractions people have looked at, and different control methods that you could embed on that side of things. Why did you choose this for the specific task, or do you think actually it's a more general action abstraction that could be useful for a larger set of tasks?
Yeah. So the argument here is more that if you have shared control formulations like this one that you use for in shared control, since you've already put in the effort of designing these mappings and constraints, you can leverage this effort into reinforcement learning to allow the robots to learn those same tasks in the real world. So you could argue that it also takes effort to design the rewards, but I would argue that the effort that you put into designing the constraints is actually, it might be comparable, but at least you have faster and more efficient learning.
Yeah, I agree with that, but I rather meant, I mean, this is becoming common practice to do these abstractions and embed constraints in the action space, we call it. I'm just wondering why the specific, because I'm interested, I work on that side, in a specific way of embedding constraints. Yeah, exactly.
Okay.
Yes, yeah.
It's a good question. I mean, because we believe it's quite efficient representation. It's a lightweight and efficient representation.
Okay, for the tasks. That's
exactly.
Okay. Thanks.
Okay, let's thank the speaker again.
Hello everybody, I'm Stephane. I'm at our work on representing position information with word models. Word models are systems where we provide high-level observation and we extract latent representation, and we ensure that we have dynamical consistencies between the latents. This then allows for latent planning. We deploy word models in the context of object manipulation, in which we provide a positional coordinate as a target. And we noticed that word models don't work at all in this double context, and is actually a challenge in the community. We analyze the issue that there are the underlying issues, and we propose a solution which will rely on providing the target directly to the policy instead of providing it through the word model. We propose two flavors of this solution, which one is based on the direct encoding of the position, and one based on latent encoding. If you want to know more, come by the poster.
Okay. With Ego Mimic, we sought to answer one question. How can we effortlessly scale up robot data? Our thesis comes down to this idea that egocentric human data is basically robot data if you use it correctly. With our system, you can just wear a pair of Project RA glasses while you go about doing any task, like folding your laundry or making a coffee. And the ARIA is going to record observations, which are these RGB images from the first-person view, as well as actions, which are future 3D hand tracking. When you think about it, this exactly matches the modality of robot data. Put side by side, you can see human data on the left coming from our RA system, as well as robot data coming from a teleoperation system. You can see that they're super similar, both visually and semantically in terms of their actions. Our algorithm Ego Mimic enables seamless co-training on these two data sources. So at a very high level, Ego Mimic takes hand and robot data, it individually normalizes them, passes it through a fully shared architecture, and then there are true losses depending on modality. For details, let's come to the poster and I can explain. And so we evaluate on 3 challenging tasks. Beginning with the toy and bowl task, this requires precision to pick up a toy and dexterity to empty out the bowl. In the laundry task, we require bimanual coordination. And finally, in this groceries task, we require constant replanning to fit the chips into the bag, which is constantly moving around. What's really exciting is that performance continues to scale as we add more human data, strongly outperforming a baseline trained on just robot data. Thanks so much for watching, folks, and please come to our poster.
Okay, hi everyone. I'm I'm here to introduce our work, Human Agent Joint Learning. And our work is basically trying to solve the issue of teleoperation. So we think that the traditional way to collect data is not very efficient. You can see the video here to show that teleoperating and shadow hand is not easy and it's not sample efficient. And here we introduce a way to use an assistive diffusion model to help us to collect the data. And if you are interested in the detail, please go to our poster session. And here we show the result that with our assistive agent, our data collection is more faster and the success rate improves and the data collection speed also increases. And we also show that when the data accumulates, the assistive agent performance is also getting better. And we also did some real-world results showing that our system is also suitable for real-world execution. And if you are interested, go to our poster session. Thank you.
Hello, good morning everyone. So my name is Eli. I'll be talking about the role of the action space in robot manipulation learning and sensory transfer. So when we try to learn a policy for manipulation, I don't know what happened to the slide, we typically have some controller trying to abstract parts of the control, the action generation that should be done. So the policy outputs some abstraction and then we map this to the lowest level of control. So in this work we try to study this choice. So we have 13 different action spaces, different controllers, different interfaces, and we take two manipulation tasks. One is just a simple reaching task, no interaction, and the second one is pushing, so there's physical interaction and context. And we try to understand how this choice of abstractions affect the learning and the sensory transfer. Briefly, in simulation, we see, you could look at the right, like these plots. You could see that Cartesian action spaces have a better exploration behavior compared to configuration space control. And controlling higher order derivatives also lead to better exploration than lower order. So this is velocity versus position across Cartesian and joint action space, 13 different ones. For Simtheory, we see that the performance is affected by the choice of the action space. So different action spaces lead to different Simtheory transfer behaviors. And one property we see is that the action spaces that control higher order derivatives tend to have a better Simtheory transfer. Then we looked at characteristics that are beneficial for Simtheory transfer. And what we saw is that action spaces that keep the tracking error low in simulation lead to a better Simtheory transfer, as you can see here. So whenever the tracking error is low, for instance, in the bottom plot, you can see success rate stays high. Yeah, this is more or less it. So please check out our Agrawal paper and come to the poster for questions. Thanks.
Hi everyone. Hi everyone, today I'll be presenting Dynamo, which is in-domain dynamics pre-training for visual motor control. So most of the common visual backbone for robotics include end-to-end learning from scratch, which does not utilize full observation data, large-scale pre-training, and self-supervised pre-training. So let's take an example of the block push environment to see how current in-domain SSL methods do. As you can clearly see, we can embed this query frame with an encoder, and we've tried to find out 20 nearest neighbors across the demonstration. And we see that most of the current SSL methods either focus on the robot or on the scene rather than focusing on the object. So can we somehow embed the dynamics info from the demonstration? This is how our method performs. It focuses more on the object rather than focusing on the entire scene. So this embeds a causal structure in the demonstration. So our model has in our model we together learn the encoder, inverse dynamics model, and the forward dynamics model. these are some of the results in the simulated environments which we get, and the most impressive result which we achieve is on our Allegro hand environment, where we are able to get policies generalizing over 20 centimeters to 10 centimeters with just 6 to 7 demonstrations for tea picking and sponge picking tasks. So with as few demonstrations as 6 to 7 demonstrations, we can use this for behavioral cloning as well as reinforcement learning algorithms. So these are some of our baselines. Please visit our poster to learn more about our work. Thank you.
Or imitation learning. A key.
Hello everyone. We introduce
in this video, we present the
Robotic hand. Yeah. I'm from Stephane Doncieux.
biomimetic hand design for Dexterous.
He speaks better than me, so that's why.
Manipulation research are driven by high-quality real-world data collected through learning from demonstrations or imitation learning. A key trend is the use of low-cost teleoperation systems for this data collection. Despite progress, the development of dexterous teleoperation is hindered by the limited availability of suitable hand hardware. We review popular multi-fingered hands used in research, noting their challenges such as high costs, maintenance, limited dexterity due to under-actuation, and bulkiness. We introduce an alternative option, the rapid hand, an affordable, fully actuated, biomimetic robotic hand with 5 fingers and 20 degrees of freedom, DoFS. Its design features an anthropomorphic actuation and transmission scheme, optimized motor layout, and structural configuration. The hand includes a universal phalangeal transmission scheme for non-thumb fingers, enhancing dexterity through anti-joint movement. It also features an omnidirectional thumb actuation mechanism. Utilizing off-the-shelf 3D printed components ensures that parts are easily replaceable and reparable, reducing maintenance costs. Performance is assessed using 2 metrics, thumb opposability volume and manipulability ellipsoid volume. We built a teleoperation system incorporating a UR10 robotic arm with the rapid hand as the end effector and an Apple Vision Pro for capturing the human hand's moves. Qualitative evaluations included multi-finger retrieval, ladle use, and human-like piano. Results suggest that the rapid hand's fully actuated 20 DoF design offers promising capabilities for dexterous teleoperation. Thanks for watching.
And if you have more information, you can contact me on the poster. Thank you.
Max, and we're here to present AnyRotate, gravity invariant in-hand object rotation with sim-to-real touch. So harnessing rich tactile information for general robot dexterity still remains a significant challenge. Existing work often reduces the high-resolution tactile data to low-dimensional representations. So in this work, we explore the benefit of utilizing rich tactile sensing for in-hand manipulation. So our method first involves training a unified policy in simulation using the teacher-student pipeline. We then train a tactile perception model to provide the tactile observations used by the trained policy. So visualization of our tactile representation is shown. So our policy is trained using simple objects, but can generalize to unseen objects of different shape, size, and mass, and also in any hand direction about any rotation axes. It can also detect unstable grasps and provide a reactive behavior that improves on the robustness of the policy. And finally, we deploy this on a continuously rotating hand. So if you're interested to know more, please come to my post. Thanks for listening.
Same one again. Okay, so this is DexiTac, soft dexterous tactile gripping. It's work done by Cheng-Hua Liu in the first year of a PhD. Resulted in a publication in Transactions on Mechatronics. So our lab explores integrating vision-based optical tactile sensing into robotic hands, and we make the robotic hands as well as the tactile sensors, as well as doing the control. So this was a foray into using pneumatic actuated grippers. So it's an 8-DOF gripper with bellows for actuation, with a vision-based tactile sensor integrated into the fingertips. I suppose one conclusion, well, I'll come to the conclusion in a minute. So in this work, we use the Digitac, which is a customized version of the Digit tactile sensor, where we converted the skin into our type of skin, which is a 3D printed skin called TacTip. In this work, Cheng-Hua customized the PCB board and put a new camera and miniaturized the tactile sensor as well to fit on this pneumatic hands, because pneumatic hands don't have a very strong gripping force. And then to complete the feedback loop, to do a variety of dexterous tasks, we use simple methods which are taking features from the camera, from the optical images, tactile sensor, to do various twisting, etc. tasks. Legacy of this work is this same tactile sensor was developed into the tactile sensor that was used in Max's work that was shown in the previous slide. And another legacy of the work is we're going to focus less on soft robotic pneumatic hands from now on, and its initial foray, and concentrate more on tendon driven and fully accurate. Thank you.
Hello, I'm Xiaolong, and I'm going to present our work decomposing the configuration of an articulate object via graph neural network. So our paper presents a graph-based model for understanding articulate objects that enables the effective robotic manipulation. The model learns the part language embeddings of the part names and the link connectivity and join states and types. So our method can be operated into 2 steps. The first step is shape embedding creation via DVAE, and the following step is a message passing neural network. So we finally got our final outputs. So here is the overall performance of our model. Our model, as you see in this table, we get over 90% for the most of the criteria, and we also conduct an initial experiment with an RL agent by comparing those with articulate information and those who do not leverage the articulate object information. So for the discussion, we like to talk about our future work that provide these kinds of information through the text prompt input in the OpenVAI model. Thank you for listening.
Hi everyone, I'm Alap and I'm going to present our work on learning to accurately throw paper planes. Even for humans, throwing a paper plane accurately at a target is a challenging task, and it takes a lot of luck given the unpredictable aerodynamics of a paper plane. This is from Munich, by the way. In this work, we are focusing on robot learning to accurately throw paper planes at a target. We don't have a robot there yet because this is an ongoing work. But our proposed method combines reinforcement learning and trajectory encoding. So we use a VAE to encode previous throws and use reinforcement learning to learn initial launch conditions. We train the policy on a variety of paper plane designs to simulate the variation found in real-world paper planes. We use Mujoko to simulate the paper plane throws, and our initial results show that our proposed approach learns to throw the planes at the target, and also including previous trajectory information improves the throws, but it does not work well if the paper plane is designed poorly. Thank you for listening, and if you are interested in learning more about it, please visit our posters.
Hello everybody, my name is Reed. We talk about deep hindsight diffusion by hybrid soft-actor critic for 6D non-freehand manipulation. As the name suggests, this is a 6D manipulation task, starting with the target pole on the right. The robot have to do the poking and match the final pose. So below here you can see is, for example, the task may rotate the cube for 180 degrees. So for the given point, there exists two solutions for it. So it needs to have like the motivation to have a more expressive policy that can have a multimodal, multi-solution. So given object manipulation from a point cloud with the RS setup, making an action and feedback. So with the current baseline given a point cloud, with the goal flow and the segmentation, go through the actor and critic. The actor will give the parameter for the action, and the critic will give it. But in this work, they only use the deterministic policy. So our work integrate the diffusion policy on top of it, and together with the entropy incorporated for continuous action, and also with the discrete location. So the results is show a good unseen category and unseen instant. It also show a good performance on the real robot setup. So it's supposed to be a video. There's show diverse action. So if you're interested in our work, so come check out my poster. Thank you.
Hello everyone, so I'm Georgios, and I'm going to present Miles, making imitation learning easy with solid supervision. So Miles leverages just a single human demonstration, as you can see here, for example, in the video to the left, where the human demonstrates how to use a key to lock a lock. And then from that demonstration, the robot can automatically learn Dexterous policies that are vision-based fully autonomously by basically leveraging just that demonstration. So what does Miles actually achieve? It can learn Dexterous tasks from a single demonstration. It requires only one environment reset. So compared to most common reinforcement learning methods that might require a human to repeatedly intervene to reset the environment to some initial state. And importantly, it also learns from scratch. So it doesn't require any prior object knowledge. It achieves this through self-supervised data collection. So at its core, given the human demonstration, which is the blue color here, Miles collects self-supervised data that demonstrate to the robot how to return to, and then follow that single human demonstration, and then we'll leverage that data to train a behavior cloning policy that allows us to learn fairly complex tasks ranging from locking a lock, USB insertion, placing bread into a toaster, opening a lid, or picking up and throwing markers into a bin, for example. So if you're interested to learn about more, come speak to us at our poster. Thank you very much.
So yeah, hi everyone. I represent TechX, a framework for simulating JSF tactile simulators. So the idea is simple. Tactile sensing can be really useful or even essential for fine and dexterous manipulation. And yeah, there are multiple tactile simulators, but the problem here is that it's unclear which simulators best, and it's because like they use different physics simulation, different simulation backends, and it might just be task dependent. Another problem is they are often not inside general robotic simulators, which means they lack features, and this limits the usability for further research. So yeah, this is why we developed a new framework. The goal was basically to combine soft body and visual tactile simulators in Isaac Sim. Isaac Sim because it has a wealth of features, and Isaac Lab for reinforcement learning, and we focus on modularity and extendability. So here's the framework overview. We use like state-of-the-art tactile simulators and physics for the physics simulation. We try to use conformable body simulation of Isaac Sim, but there were some problems, like for example static friction, which leads to us being unable to pick up objects. Compared to this, we integrated gRPC, which has like proper friction handling and is extremely stable. We also got multiple demonstrations, like Bäuml experiment, and free reinforcement learning environment. Yep, thanks.
Hi everybody, I'm Albert, and today I'm going to be presenting our work Drop, Dexterous Reorientation via Online Planning. So the question, counter to a lot of other works in this workshop that we want to answer, is whether sampling-based MBC can compete with RL in contact-rich manipulation. And so to do so, we studied this classical cube rotation task where you simply just try to rotate the cube as many times as possible to hit goal orientations in a row without dropping. And so back in 2018, OpenAI managed to do this in sim-to-real zero shot using only domain randomization in RL. So in contrast, we're interested in this very simple class of methods associated with recent tools like Mujoko MPC that have shown a lot of promise over a wide range of context-rich manipulation tasks in simulation. So the question is, does this transfer at all in hardware? So it turns out the answer for this task is yes. So the drop architecture is built on top of this sampling-based predictive control strategy, which kind of works like this. So first, you sample some batch of open-loop control rollouts from any sampling distribution, and then based on the cost of those rollouts, you can just choose what to execute online and also how to update the sampling distribution. So super simple. And we tested, again, two very simple instantiations of this. The first is predictive sampling, where both what you execute and the mean of the sampling distribution is simply the best rollout. And then the cross-entry method, which is essentially the same thing, but over the average of the top K rollouts instead. So really surprisingly, it turns out that CEM is able to achieve some incredibly dexterous and very contact-rich behaviors that are about as expressive as what you saw from all these recent reinforcement learning-based methods. So I have a lot of insights, and if you're curious about any of these, then come visit my poster.
Hello everyone, I'm Yunshu. Today I'm going to talk about our work, ATK, Automatic Task-Driven Key Point Selection for Policy Transfer from Sim to Real. With the recent advance in computer vision, key point representation is more and more robust to visual variations, occlusions, and distractions. However, how to leverage this representation for policy learning is still a problem. So based on our work, we found that a task objective could inform the selection of this representation, and also the desired set of key points is the minimal set of points that can express the optimal policy. And here's our method overview. We utilize a task-driven information bottleneck, which is a student-teacher architecture for a key point distillation and also the policy learning. So with this process going on, the input key point will be automatically masked out or recovered through this process. And after this process is done, the final set of key points will be chosen and the optimal policy will be learned. And also, after this key point will be selected, after the key point was selected, those key points can be transferred from sim to real, use a correspondence function, and the policy could be deployed in zero shot. We show that our methods select task-driven key points even within same object for different tasks, and also ATK, our method, enables transfer policy to remain robustness and generalizations to different environment disturbance, for example, the background change, the random object introduction, and also some random light change. So if you are interested in our work, please stop by to the poster section. Thanks.
Hi, I'm Kenny. I'll be presenting bimanual dexterity. Many tasks demand the use of two human-like hands, but teaching by manual hands is challenging. To address this, we developed Bidex, the system that effortlessly completes highly dexterous tasks in real time. Bidex uses a teacher arm connected to a motion capture glove worn by a teleoperator. You can see the teleoperator behind there. The teacher arm data is mirrored to any standard robot arm, and motion capture glove data is retargeted to our 21 degree of freedom leap hand. Compared to vision-based approaches such as the Apple Vision Pro, we find our system is much faster to teleoperate with, more intuitive, and collects higher quality data for behavior coding. This enables significantly more complex dexterous tasks, such as drilling, spraying a bottle, or using a spatula, and using a variety of different tools. The complete Bidex, which includes the two X arms and the leap hands we used, is priced under $30,000. We've open sourced all the code we use for the Manus gloves and our leap hands, and all the code we use to retarget the data to our robot hands. We use Leap Hand V2, which is a hybrid rigid soft hand that is compliant and not brittle, yet very strong. It achieves this with a 3D printed fingers that have TPU on the outside and PLA on the inside, which acts like a bone structure to the fingers. It's extremely dexterous with 21 degrees of freedom, and it's very easy to assemble, costs around $3,000. Thanks.
Hello. Yeah. Hi, I'm Lars, and I'll present our work on residual RL for precise assembly. So, imitation learning is an awesome way to teach a robot arbitrary new skills very quickly. We find that the resulting behaviors are brittle and not reliable, especially when precision is needed. And of course, you can always throw more data at the problem, and we find that that helps to a certain point, but performance saturates at suboptimal levels. So what we find instead is that we can take a pre-trained diffusion model with action chunking, and then add a closed-loop procedural correction small LP, and train that with online RL, which gives a much more reliable policy. And this combination allows you to both solve very long horizon multi-step tasks that require precision, and and across a range of different tasks we find very, very big improvements of success rates. We also transfer these behaviors to the real world through co-training and policy distillation to operate just from vision. And happy to talk more at the poster after this. Thank you so much.
Thank you, all the speakers. Hello. I'm excited to have the next speaker, Xiaolong Wang, from UCSD and NVIDIA. So he will talk about dexterous manipulation with real and sim data.
Okay, thank you for coming. The title is quite simple. So I just want to discuss about, talk about some thoughts on how to. There's a lot of discussions on using real data or using sim to real. So I just want to talk about how I feel about how to combine this kind of data in training for dexterous manipulation. So about simulation data, simulation sim to real is really, really hard. So this is some old work we did that we basically train RL policy in simulation and transfer to the real world. We're using point clouds as observation at that time. The handles is a little bit strange because that's what RL do. But essentially that's one work, and then this is another recent work that we basically say, we not only just want to do teleoperation in real, but also can do teleoperation in sim, and then combine these two data. So if you notice about all these tasks, it's not that exciting. So that is what I've been facing for the past 2-3 years, is that whenever we try to do things with sim to real, the task is just a little bit boring, because you kind of need to align the simulation with the real in certain level, then only then sim to real transfer will work, or sim and real data compilation will work. So that is the constraint we have. And then I look into all these cool people doing all this teleoperation thing or collecting real data. Everything is just looks so much better. So that make me wonder whether I should do something in that direction as well. So that's essentially why we start this work, which is also presented in here. And we had a demo for the first 2 days. It's the open television work. Basically, we try to also explore these directions of doing basically teleoperation. And the thing we did a little bit different from the previous work in here, where you're using a VR to control, but I really like the part that it is actually having an active perception. So if you look one more time, so we wear Vision Pro as your people's head is moving, the camera of the robot is moving at the same time, and then you essentially try to stream what this exact camera has been seeing to the VR in real time. So this is the robot is seeing the back of the head of the operator. So our system kind of basically use Vision Pro to capture the hand pose, and then we do head pose retargeting, and then that basically controls the robot to do this teleoperation with hands, and there is also real-time visual feedback to the VR system, and the head is basically active. So this allows, so we actually have demo here, but I didn't put it on the slides. But essentially, it's doing similar idea that we can actually do very remote control teleop. So this is girl from MIT is actually controlling the robot in UC San Diego to do tasks. And basically, you have the visual real-time streaming to the Vision Pro in there, and then this pose is also real-time controlling the robots in here. So we did a similar demo in here. Basically, we control our robot in San Diego from Munich. So that is even further away. So that's basically we collect some data, and then we try to do some imitation learning. We didn't collect a lot of data, so at that point, so it's really just this particular soda and then this particular box. But we're able to basically kind of overfit these scenarios and do reasonable continuous tasks, keep inserting the cans into this container. So it's quite simple. So basically you have image input, and then you have a pre-trained network, and then you do imitation learning. But I like the part I like most is basically, it's not just the action of the hands or the arms, but also the action of your neck. So it is actually providing active vision. You are basically seeing as you are operating at the same time, and this is also I'm also from a computer vision background, so I work a lot of all these video understanding, action recognition and things during my PhD. So this also reminds me a lot of egocentric videos. So it looks very much like those videos, but with a robot hand. Yeah, so this is another task because since folding is popular now, so we also do folding, and then you can keep folding. But the same tower again, we didn't collect a lot of data. So that was imitation, and this is the actually teleoperation. So this is basically showing a little bit extreme on how actually, although the Inspire hand is, I mean, a lot of people use it, it's not that great, but we can still do relatively dexterous tasks like this, like opening a small box, putting things inside, and close it. This is actually only enabled because of this egocentric view. So we find this streaming the egocentric view to the user is quite important. We have other teleoperation system that basically you are seeing from the third-person view. You can use exoskeleton operating here and then seeing what the robot do there. For that project is ACE, which is also presented in CoRL. I asked students, can you also do the same demo using that system? He said he's not able to do it because it actually requires you to have this egocentric vision to operate this kind of task. So very important to have this first-person view. And we have some drilling. I show this is only because if you work on 60 pose estimation, you always need to estimate the pose of the viewer, but nobody is using it. So we basically actually try to use it. Here is one demonstration. So there's high precision control, which also again is enabled by the first-person view. So you are able to put something in here. Although it's not entirely the right thing to do, it's not supposed to touch, but it's the best you can do so far. So some thinkings about teleoperation. It's great, but then it also takes a lot of effort to collect data. Very tired. So wearing a VR glass, like usually students do maybe 20 minutes, then you don't want to do it anymore for the day. So very tired, a lot of effort to collect the data, so it's not that scalable in general. And then now I want to go back to simulation again, so it's kind of back and forth. So can simulation still, although it's hard, but then it still can generate a lot of data if done well. And most importantly, which is connecting to what I'm going to talk about next, is that it can explore skills that basically is very hard to obtain from teleoperation alone. So these two align the research we did on in-hand manipulation. So this is the earlier work that we did. I'm not going to talk about it because it's 1 year old. But it's the first work we did. We tried to do in-hand manipulation using reinforcement learning and then transfer the real. We have some cute design of the tactile sensing in here. It's a 0-1 tactile sensing, but that allows a small synthetic gap. So after this work, we do think that because we are essentially rotating objects have a palm holding the object, that makes things much easier. And then we, of course, a lot of you have seen very cool demo on the demo session. Don't do in-hand manipulation. You can actually hold an object in this way and robustly. So that's actually much more challenging. So it's instead of holding things upside down, we try to also push the in-hand rotation to some other task, to a more extreme case, which is, so this is a very popular video, and then a lot of people are basically kind of quite inspired by the skills can be emerged using LM and RL in simulation. And then that makes us think whether we can do kind of similar thing, but actually do it in real. So this is paper that is presented in here. So Jin, which is led by Jin, my master's student, who might apply for PhD, not sure. So and then Yin and Haizhan and Haozhi, which is the organizer here. So in this task, we are basically trying to do sim to real, at least in the first place. So the title is supposed to be learning to spin pans, but then we do lessons from learning to spin pans because if it works so well, then it's going to be learning to spin pans. But if it doesn't, it's not that well, then we put lessons. So essentially, so the thing is, initial thing we try to do, we also have some tactile design and this and that. We try to transfer this simulation skill, try to transfer it to the real world. But then it turns out to be quite challenging. So we use some teacher students, so that is quite standard in a lot of simulation simulator tasks now. So you basically have a teacher policy that you have had all the ground truth, object pose, and observations, point cloud, everything, and then you train teacher's policy, and then you have partial observations and train student policy, and try to put it in real. But that's not working. so to just show you how hard the problem is, here is some video. We also try a lot of like different sizes of like these long sticks. So we had some initial design of tactile sensor, but we eventually give up. So I don't want to talk too much about it. But this is just give you an idea that once you try to do closed loop control of this kind of task, it's just like, because the content is so dynamic and basically it's just, if something goes wrong, immediately fall, and then it's just like for example, in this case, we see a lot happen is basically once it's out of distribution, then you have a finger doing this when you do sim-to-real transfer. So quite a challenging task. The task is challenging also because you kind of need to have a large motion, so you cannot push the hand to use too much force to push it, otherwise you go down. But then you cannot be too small force, otherwise it also fall down. So that's very challenging. And then basically 2 weeks before the deadline, so students said, Jin said basically it's kind of impossible at that point. So how about we just try to do some open loop replay of the simulation task, and that works like in one round, reasonably, actually not too bad. So basically what Jim proposed is saying that, oh, maybe we can just collect real data using this open loop replay and then just do behavior cloning. How about that? So that works actually pretty good. So what we do is really just, we have the simulation policy, but we just use this policy to give us the skill, the rotating skill, and then we do open loop replay. So we don't care about the environment, we just replay the trajectory, and then some are successful, some are not, but we essentially collect a real data set out of it, which is successful ones, and then train, fine-tune the sim policies with the open loop replay data. So that basically works quite reasonably well. There are some numbers there which we use to attach some tactile sensor. We eventually remove it. So the input is only proprioception at this point. So here is another example that we are rotating different pens, basically using this approach. All right. So okay. So we keep going. Okay. Here are more examples. All these objects are kind of randomized. That is not trained in the training set, kind of generalized to different objects. So becomes very helpful once you have a little bit of real data. We didn't collect a lot of real data. It's really around 50-ish trajectories, and then fine-tune on the original policy, and then it performs quite well. So some other examples. Okay, so it's already rotating one direction though. Okay, so that's here are some failure case. It's still quite a challenging task, and in this particular failure case, is basically at some point it's trying to fall, but it's not fast enough to have the finger go to stop it. So this is one failure case, and then it's a very long thing, so long stick. So you kind of, as you are rotating, you can drift away, and then the center of the mass basically goes away, and then it also fails. So now comes back to the lessons we learned from this project. I do find deadline is an inspiration of source of creation, because it's like this only works because we are two weeks away from deadline, and then we have to make something work. So that's why academia is still important. That you don't have these deadlines, then there's no creating this work. So sim training requires quite extensive state designs for this particular task. So we do actually have, for example, initialization is quite important. So we manually defined maybe 20, 30 posts of the initialization of the SIG. So that's one thing we do, and then there are many other things that you can check the paper. So requires a lot of design. And then sim-to-real does not really quite work directly, but simulation is still very useful to explore the skills. So this kind of skills, it's kind of impossible to do it with teleoperation. So it gives you a very good initialization, explore the skills that is hard to collect with human location. And then once you explore the skills, you can use some way to collect data from the skill you explore and then do real-world training. So I think in general, I think it's just important to, so real-world data is still very important, but it's not necessarily we need a lot of them. We can certainly leverage simulation training a lot, but then we need to find the right way to use it, right? So in this particular case, I still find simulation training, it's very hard to do complex scenes. So do real to sim, digital twin, and then do sim to real that way. It's still very hard, but in this particular case, we do find just use sim to explore the skill. So that is already very useful. And then leverage real data to do the others. So teleoperation is also the same. So we can use that to collect real data, or we can use this to first do sim and then use sim skills to collect the real data. So that's an example of how we combine real and sim. Hopefully that helps. So that's all. So I'm welcome any questions.
Thanks. I really enjoyed both parts of your talk. So a quick question on the first part. You better get asked this lot. So latencies.
Right.
And then a question on the second part. I was wondering if it was down to if you've got a feedback loop, then that introduces slower cycle time, latencies, etc. Whereas if you're just playing something back, you can kind of control it at a faster frequency. I was wondering if it's kind of down to that kind of frequency of the trajectory generation.
What do you mean by play something back?
Well, because you learn the trajectories in simulation and then you play them back open loop.
Right.
So that means you don't have a feedback loop that
Yes.
takes time.
Right.
Is that basically the the issue
Yeah,
that you're
yeah.
working around? So if you have a much faster feedback loop with the tactile, let's say.
So first, there's no tactile in here. It's only proprioception. So it's only condition on state of all the motors. So this is basically open looped. There's no feedback. The thing about taking feedback is that what happens in here as well. So somehow when you try to do closed loop control, and then something goes wrong, it takes some feedback that basically goes to out of distribution for the policy you train, and then you get basically fails. So actually taking feedback can get wrong easily in this case. So we find that maybe just doing open loop control, replaying the trajectory without feedback, actually can run a little bit longer.
I suppose you had a feedback loop that was at a kilohertz.
Right.
Would that have made a difference, rather than say 20 hertz or something?
Maybe that's possible. Right. We haven't explored that. I see. Not very high frequency feedback, but low frequency feedback. Yeah, that would be interesting to try. Yeah, we haven't tried that. Maybe. Thank you. For the first question though, the latency is so if it is just like this, it's just side by side. It's not quite visible. So it's less than 0.1 second latency. And then if you are doing it from Munich to San Diego, some people have tried our demos in the first 2 days. So that takes 0.3 seconds because the transmission of videos from here to California already takes 0.15 second-ish. So there's a little bit control latency and then transmission of the videos. So that combines. You will feel the latency basically, but a lot of new, people have never played with it, can just do things with it in our demo to explore. Yes?
Hi, thanks for your talk, and it's very thank you for your open source
for the retargeting and television. Yeah. So my question is, I have a question about when we do the robot do the fine and dexterous manipulation. If you use a Wang, we don't have a haptic feedback. It means when I just like when let the robot play a task like the human-like piano playing, it's fine. Sometimes we can't have the feedback. We only use the visual loop. So for the teleoperator, for those guys, they actually don't know if they grasp it or not, they touch it or not. So what do you think? We have more choice, or maybe gloves is better? What about the, in spare hand have 6 dots. What about the more high dots, like the illegal hand? If you control illegal hand.
Right. So first haptics feedback. Let me quickly. I was actually. Sorry. Which paper? Yes, this one. Yeah. So I think in this work we do actually study the haptics feedback in here. So essentially, this is our design. So you can have this is some force sensor in here, and then you have some motor in here. So you can touch it, and then basically it moves a little bit, the motor. So that actually helps a lot. So if you have haptics feedback, like this guy in here, he's doing teleoperation. I'm not sure if it's clear, but if you have haptic feedbacks in here, actually do much faster. So that's one way to do haptics. The other way we are trying to do haptics with vision points, you can actually also visualize the touch. So you can have visual feedbacks on once this touch is, let's say it's red, and then it doesn't touch, it's green, and you can also do some of the visual feedback.
Thank you for your question. In fact, I'm curious about that. I'm not questioning you. I'm just I'm just curious about. I know that this ability hand, right?
Right.
Yeah, and the tactile sensor maybe it's not that sensitive, and it's not that accurate. Sometimes when you press the side, finger side, and maybe the thumb, another part will be activated.
Right.
So, and when you will grab it, you need.
So it's not that great. So we also did some modification on this recently. Yeah, we agree that it's not that sensitive.
So it's a hardware problem.
It's a little bit a hardware problem.
So yes, that's why. I see that because of time.
Right. Sorry.
And now our next speaker will be Pulkit. Pulkit is an associate professor in MIT, also the program chair in CoRL, and he will talk about coerced, reliable, and dexterous manipulation.
Thank you for. Is it working? Can you hear me in the back? Perfect. Kind of.
It's not open.
Hello.
Make it closer.
Closer. Okay. Yeah. So today I'm going to talk about manipulation. So I'm going to take a slightly different view. I think a lot of people are going towards generality as a way to build, better robotic systems, and I would focus more on reliability, with the general belief being that if we can make the system be reliable for one task or one environment, then it will be easy to scale it up and make it general across different tasks and environments. So the real problem is, given one task and one environment, how do we get a reliable system? Right, so think about, you want a robot to work in your kitchen, what's the pathway to make the robot work in your kitchen first? And let's not worry about every other kitchen, right? I think if we can make it work in one kitchen, then there's a pathway to make it work in many different kitchens. So this is what, prompted us to do this work, where we said, suppose you had your kitchen, you wanted your robotic system to work, then, we can, scan the kitchen. So this is, Marcel, taking a scan of the kitchen so that we can put the kitchen in the simulator. Right? And this is how the scan of the kitchen looks like. This is using the latest and greatest in Nerf. But of course, what Nerf doesn't give you are the articulations and the joints. So we made a, easy to use, API where people can add articulations, and you see the timer which is running on the bottom left. So in a couple of minutes, you can add joints, so you can get the articulations which are required. Now after this, we can train in simulation. Training in simulation means that we can collect large amounts of data and potentially make this policy be quite robust. And once this policy is trained, then we can go and deploy it in the real world. So here is the robot now trying to open a microwave after practicing things in the simulation. So how did this system work? Right, so and maybe I'll show you some more results, and then I'll go back and tell you how we built it. Right? So here's another example of a real world scene on the top and the digital twin on the bottom, where with the advances which are happening and how photorealistic simulations are becoming, it's becoming easier and easier to train policies in simulation which start transferring in the real world. And the added advantage you end up getting is that these policies end up being quite robust. So for example, if I want to put this mug onto the rack, this is a robotic system doing it, but also we are mucking up the scene in the background. So you can change things in the background, the mug hits the shelf, but it still adjusts, and then you can also move around the mug, so on and so forth. So there's nothing special happening over here. This is just the magic of doing lots of randomization that you can afford happening in the simulation. And just to be concrete on how this pipeline was working, so initially what we do is once we scan, we also collect some real world demos, and these demos are used to initialize a policy, right? And this is a policy that we then put back in the simulator. So you have a behavior clone policy in the simulator, and then we can do fine tuning with reinforcement learning. And that is a reinforcement learning fine-tuned policy that we deploy. So what we've established is for one task, that I need to do in my kitchen, I can start obtaining, some robustness and some reliability. So, what did we learn, in this process? First thing that we learned is that co-training with real-world data was important for getting simple real transfer, but you only require small amounts of real-world data, consistent with what Xiaolong was saying, just before me. Second thing that we learned is that, if you use a combination of behavior cloning in RL, for example, you had 50 demos, plus a sparse reward function, it does two things. You don't need to design reward functions in detail. You can just use a very sparse reward function. Other thing is, when you're doing real to sim, then, your scans are not going to be perfect, and there are going to be errors in the scan. So you can potentially exploit them if you did pure RL. But if you did behavior cloning, that puts a prior, which constrains the exploration of the robot. And what we found is that leads to less exploitation of the imperfect simulator which is there. And I already showed you that simulation can help learn robust policies. So the next question we asked is, can we scale this up? So then what we asked is different people to scan their kitchens and upload their kitchens so that we can start training on their kitchens. So as an example where we were trying to put dishes in the sink, and this is different people scanning their kitchens and uploading it. But then the question became okay, people can scan their kitchens, but then how can we make the pipeline be very easy to use for everyone? So you can scan your kitchen, give some demos, and then the RL training can come in and give you a robust policy that we can then deploy. So that led to our next attempt, where this project is called DART, which we recently put out, where you can with an Apple Vision Pro, and then you can start giving some demos in simulation. So here is different tasks that you can perform. It supports multiple different platforms, different robotic systems. And the vision really over here is that anyone can scan a kitchen, you put it on a cloud, anyone can come in, you can provide a few demos, and in the background, RL can keep on running. Right? So it's a data flywheel where everyone can contribute, it can fundamentally be crowdsourced, and you don't require a robot to start using this system and start collecting data, which can then be scaled. So if you're interested, we are running a demo of this, so you can go try it out. And then we also performed, many, human studies to analyze, how easy is it to use the system as opposed to many different, teleoperation systems which are, out there. So I'll just let you watch, some of the video to see that, you can do things with, simple hands, you can do things with more, complex hands. So a couple of things, that we found is, so for example, we compared, our system with the, real world Aloha teleoperation to see how well it matches in terms of the user experience, how fast can you collect data, and what we find is we can collect data much faster, and you also end up having, much lower physical fatigue, right? And then we tried analyzing, what are things which really makes it intuitive for people to give demonstrations. And the main thing that we ended up finding is that if you are in the VR world, then your experience is really intuitive. For example, if you're teleoperating a robot, you can't look from different viewpoints. So if you're picking up small objects, for example, you don't even know where your hand is. And the discussion previously was happening, okay, what about tactile, right? I mean, tactile teleoperation still remains hard. But the point is we're not depending on teleoperation to collect large amounts of data. We just want to initialize something so that RL can come in and then improve over it, right? So the main thing is if you can minimize, lags and you can make the visual experience of the person be intuitive, then you can collect data much faster. And people also end up enjoying it much more. And in the paper, you can find, results on the throughputs that you end up getting using the system. If you want, you can use a system also to do real world teleoperation, or you can also do teleoperation in simulation. And people voted with their feet, saying that I felt much more comfortable to use the system. But don't believe my slides, go test out the system, which is outside. Great. So, what did we gather from this? What did we learn? So the one thing that we gathered is, in the first part, I told you how we can build a real to sim pipeline in which we can start training policies. Right then, the question is, okay, how do we scale it up? So now we have the tools to scale it out, right? An API from which we can do real to sim scans, and the other API with which we can give demonstrations. Some open questions, still remain in this. One is, what are the kinds of tasks that we can perform in simulation? And this is something that we are really pushing on, even going to things which are deformable, things which require a lot of precision. The other question is, suppose if you wanted to build an open source, robotics foundation model relying completely on crowdsourcing, then what could be incentive mechanisms to have people come and participate in the platform? Right, so those are some, exciting and interesting questions to be considering. Now that we had this pipeline, then we said let's apply this pipeline to a diverse set of tasks. So we picked up, a bunch of assembly tasks where you can use the framework I described. You put things in the simulator, you give some demos, and then you use reinforcement learning in simulation to start performing these tasks. So all of these tasks require a certain amount of precision, but they're also long horizon in the number of steps that you need to be performing. So now to do some comparisons, so if you just did imitation learning, for example, this is what these plots are showing. Right? If you do vanilla BC, it really doesn't work. If you end up using the latest and greatest advances, which is the chunk behavior cloning, that ends up getting reasonable performance. But even if you go until 100K demos, the performance ends up saturating to around 75 to 80%. Right, so there are two things which happen in normal behavior cloning. One is the demonstrations are being provided by a human, and you're not able to query an expert, you're not able to explore yourself. So if you do Dagger, then the performance definitely improves because you can account for the distribution shift which is happening. But the second thing we also observed is that because modern BC methods end up doing chunking, it means they're akin more to planners instead of being controllers. Right? Typically when people are running BC systems, they're running at 10 Hertz, but then also you have an action chunk which is 10 actions, which means that you're running open loop for 1 hertz, right? So what we essentially did in this work is to add a controller which is running at much higher frequency. So you can think of BC as providing a plan, and there's a controller which is learned in simulation which can correct for any errors which are happening in that plan. So which is what we call reactive control. So on the left you're seeing the system trying to perform a precise task with just BC. You can scale it up to 100,000 demos. It wouldn't end up becoming as good as you could get by adding this layer of reactivity. So to illustrate this more with a diagram, so you have pick your favorite behavior cloning policy, which is running at 1 hertz because that's how things are today. And then you can add this residual correction, which is trained using reinforcement learning. And then we can see how much the performance improvements is across a range of tasks, and we do end up getting substantial improvements. Again, starting to get into high 80s, high 90s. So this is quite exciting, and we are hoping that we can keep building towards it. Now there are 2 things which are still there. One is or the main thing which I'll focus on is, we are getting up to 90%, 95%, but that is still not, 99%. So how do we end up going to, 99%? And one of the things is that all of these works are really relying on, only visual feedback. But if you think about it, a lot of these tasks are really about, feeling things, right? And we just don't have any sense of feeling, any sense of, proprioception that we are utilizing over here. The second degree is that all of these hands are quite simple, right? Which means that even if you do the task, these tasks can become quite long horizon. And then there are some tasks, like people like to talk about, which are just, quite hard to do if we just had, simple grippers. So in a parallel, line of work, we have been trying to push, this direction, and this is, somewhat old work, but I'll just, present it just to say that how everything connects together. So this is, we are leveraging the same framework of training in simulation, but now with multi-fingered hands to see if the same approaches scale up, and we can use these techniques and then transfer them into reality, right? So for example, here we want to rotate this object to the orientation shown on the top right, and here's a camera observing it, and then the system ends up reorienting the object to the configuration which was desired. So this is what we showed is possible last year. But as Xiaolong mentioned, these sim-to-real systems are not perfect, and neither was this system perfect. The success rate was close to 60 to 70% in this instance. But we can reuse the same system for doing different tasks. So here is using the same reorientation controller now to perform vegetable peeling. With the reorientation is trained completely in simulation, and now by leveraging proprioception, you can also resist the forces as the second hand is coming and trying to peel these vegetables. And this is an example of some of failure modes which can happen. For example, the object drops down. And this really forced us to think about the last missing piece. There might be more that we're not aware of, which is trying to include some notion of tactile, but also thinking about the manipulators that we're using, what is the right kind of compliance that needs to be there. And that led to this new hand that we have been developing called the eyesight hand. So this hand is compliant, but we can also control the compliance of the hand, so you can make it stiff or you can make it loose. It is covered with tactile sensing, and these are gel site sensors that we integrated. So I'll show you what this hand can do and how this hand is designed. So first we're just showing some degrees of motion of what this hand is capable of doing. Many of you are probably aware of gel site, so that's not a new technology. But gel site is quite sensitive to looking at different kinds of features, and we made some modifications with gel site, and this is where you see the compliance of the hand. It's not rigid. Even if it collides with the table, it will comply, and this is something that you can also control. So then we can start studying, how does, this compliance and ability to access tactile start improving performance. So here are, some tasks. For example, we want to open the cap of a bottle. If your hand tries to do it only with vision, at some point you're completely occluded and you can't even feel the cap, versus if you end up using tactile, of course you'll feel the cap and then be able to open it up. Right. Similarly, here's an example of after peeling vegetables, you perhaps want to chop vegetables. So I showed you peeling before, but this is peeling with a vision-only policy. And the hand gets there, it picks up the knife, it comes to the vegetable, but as it starts cutting, it cannot feel the forces, right? So things end up sliding. Versus if you did have access to tactile sensing, ability to feel forces, the system ends up being more reliable, and this is something that you'll see in the video. And there are numbers which are in the paper that you can look up. So this is all great, right? So now what we have is a hand that we can start using, start training in simulation, but some of you also like to train in the real world. So to enable that, we also have this project Dexo, which puts this hand in form of an exoskeleton. So if you want, you can go and start collecting real data with it to initialize your RL policies. So here is Dexo in action. So this video is playing in real time, and we're trying to assemble the hand itself. So this project was led by Haoshu, who is on the job market in the coming year. So the idea of this hand is that first you can feel some forces because you are not doing a virtual teleoperation, so you have some sense of forces, but you're also recording tactile data and vision data as you're performing these tasks. So there's a possibility of actually creating a truly multimodal data set for manipulation, both in the real world and hopefully back in the simulation. So I'll let this video play, and I'll open it up for any questions. The short summary is I'm pretty excited about this pipeline where you come in, scan your environment in, give a few demonstrations, then use the power of RL to make it be very reliable in one environment. And we can do it with simple grippers, more complex grippers, with different kinds of sensing modalities, and then thinking about how we can eventually scale it up. So thank you so much for your time.
Okay, let's just have one question because of time.
For the great talk. I just have a question about the real-to-sim system. So there's also some past work on environment generation from scratch using like VLMs or 3D generative models. So I was wondering, what are your thoughts on those kinds of environment generation versus reconstruction for real-to-sim?
Yeah, I think it's a very I think the generative way of doing things is an excellent approach. I think the challenge is the kind of complexity of scenes that you end up getting is much lower at this point. So I think really the reason to do real-to-sim is to capture the real world diversity. But if those approaches catch up, then it's great. Other way you can think about it, the way we're doing real-to-sim is generating the data to train a generative approach in the future.
Thank you.
Our next speaker would be Berthold. So, Berthold is a professor in PUM, which is this school, as well as DLR. And today he will talk about autonomously learning AI towards human-level manipulation with Dexterous hands.
Yeah, thank you for the introduction. So my voice is a little bit damaged, but I hope it works nevertheless. So yeah, we are a joint lab with TU Munich and the DLR Institute of Robotics here nearby Munich. So the goal we are heading for is performing dexterous manipulation using humanoid robots, and here I will mainly talk about the hands, but to have a little bit look back a little bit. So what we did with the system already 10 to 15 years ago is seen here. So it's classical AI, meaning the combined advanced mechatronic system we built back then with vision system, classical planning methods, so no deep learning involved yet in this thing. So that's what you can do with classical AI. You can also hear this, I think, quite famous demo of catching balls using only onboard sensing, and the hand is fast enough to really catch the ball. So this is also based on classical vision and real-time motion planning performed simply by having enough compute power. And you can also play catch if you have two of those robots. But this is not what we think, or what the real difference you can make with learning is when it comes to dexterous manipulation. There are classical AI methods, in our experience, did not work out. So dexterous manipulation, and there we always think of mainly hands. So the human we want to take as the model. You have the human, it's born, and after some years it can do amazing things, from body control to whole body manipulation. So having control over all forces, also have a high level task planning, so how to grasp things in confined spaces, to move it around without breaking the grasp, down to fine manipulation, where you really use strategies to overcome your tremor, to do delicate tasks, and all with one hardware at hand. So you have the sensors, of course, vision and touch, and you have the motor skills, especially in the hands, many degrees of freedom. But then you have this general learning machine and almost no prior knowledge, and you can continuously adapt. So this kind of tasks you do mainly by testing out the world and learn from interacting with the world. And this is a way we wanted to go with our humanoid system. So we built a system which has all the sensors available, vision, touch, all the motors, especially in the hands, I will show you in a minute. And computing resources is easy to couple nowadays. Even you can go as high as you want with cloud computing. And we can already do some tasks, as I've shown, so catching balls, highly dynamic, handling up to 15 kilograms in manipulation, and then this more towards fine and precise manipulation. This is then where the learning methods are necessary. So the hands we are using are multi-fingered hands. They are more than 20 years old now, but still I think one of the most advanced hands are available. Torque control, 12 degrees of freedom overall. And what was missing for more than 20 years now was the intelligence in the system. So hands are too complex to teach in our experience. And what we used them mainly for was telepresence, where the human was in the loop as the providing the intelligence. And that intelligence is needed for hands is also obvious when you look into the brain. So the human motor cortex is here marked, and then you see that the amount of neurons used for the hand is really amazingly high. Okay, vision, the skin, the face, and the tongue. So we are social beings. That's also important, but compared to the arm and the rest of the body, the hands are really the important thing. And this is also this famous homunculus. We are basically hands animals where main part of the brain is used to process the hands. So intelligence and dexterity with hands is something you have to come together to in the end be dexterous. So what we did with our approaches up to now, from starting 2-3 years or 3-4 years ago, using these modern learning-based approaches. And learning means for us always autonomous learning, so starting from first principles, doing things in simulation, but not collecting data from the real world and doing imitation learning or look at videos. So it's all based on first principles and so hard facts, so to say. So the first thing is what you can do with a hand. What you cannot do with a two-finger gripper is grasp arbitrary objects robustly. So, but then you have a problem. If you have a robot and you have your object, then you see the object only from one side. As a human, you know how the object looks at the back side from experience, and that is what we train the network for, kind of a foundational model which can complete shapes from one view to the full 3D shape of the object. And so all the objects you will see in the video are not part of the training set. This is generalization. So it's trained on ShapeNet. We can then the second thing you have to do is you have to come up with a correct grasp. So having a robust grasp means you really want to have using the full palm of the hand, so you have to take into account many contact points. And if you would do so with a classic grasp planner, it would take minutes to compute a grasp, if not longer. And what we did, we trained a network which then can directly predict the orientation, the optimal pose of the hand relative to the object, and the 12 degrees of freedom for the finger configuration. And the training data set we used for this is generated with a self-written grasp planner, which is high fidelity because we don't have to make approximations to be fast at online processing. We can do it in a very principled way. And this high fidelity data set is then used to train this neural network, and the grasps we are generating can be directly played onto the hand without any post-processing, and leads to very robust grasps. So here, depending on the shape of the object. So we put in this shape completed object, and the result is this grasp. And we can, depending on the object, the grasps are very different and natural, but each time the most robust grasp are very close to the optimal grasp. And this also works for very different, and it takes altogether below 1 second to predict from looking at the scene the grasp. And it works for very different kinds of objects here. And so you see, even if there's only a small amount of data available from the 3D sensor, we nevertheless can robustly grasp the objects. Another thing you can do with a hand you cannot do with a two-finger gripper is dexterous in-hand manipulation, where we've already seen some very impressive examples. So it's something we as a human do all the time. We grasp objects from the table, then you have to reorient it to move it robustly to a certain location, and then, for example, we have to hand it over to a user, so we have to reorient it again in the hand. So something we do all the time, and also in industry, that's something people often do. And the classical example and benchmark for this is this famous rotation of cubes. So we did the first time, we were the first ones to do it upside down, so the way harder way to do it, always force closure is needed. And we use deep reinforcement learning to do so. The special thing in our work is always we are not doing any reward shaping, so we use a vanilla reward, or we always try to. So in this case, it's spinning in the right direction is good, and dropping the cube is bad, and nothing else. So that one then we train from scratch without initialization from human demonstration, really random initialization. After a while, it learns that grasping is a good idea to get rid of the dropping penalty. A little bit more time it rotates as far as it can go without regrasping, and then it takes a little more time to really find out that you can regrasp and then rotate the object even further. And this takes only about 5 hours, so it's really fast to do so. And the simulations we came up with are good enough to do 0 shots into real transfer to the real system. The important thing is it's all purely tactile, so we are not looking at the scene. It's based on the position and torque sensors in the joints of the hand. So this makes it fundamentally harder to perform this task, but this is what you have to do, in our opinion, if you do in-hand manipulation, because you usually cannot look at what you are doing with your hand, and that's also what the human can do. And it's also robust, so we can change the orientation, although it was not trained for this orientation, so it's a robust strategy. If you compare this to the seminal work of OpenAI, they use this upside palm orientation, which is fundamentally easier. They used a full camera rack for tracking the state of the cube, and it took months of training on a GPU cluster. I think at least millions of dollars. So we do it in the harder task, purely tactile, 5 hours on a single GPU. Cloud computing costs about $1.50. So there's some advances in this field, so to say. And the next thing we did is we also made a modular architecture for our reinforcement learning system. So when you can manipulate the objects, it's not enough to do more interesting tasks like stop in the right moment. So if you want to reorient it to a specific orientation goal, you have to know about current state of the object. Not only you have to know how to move the fingers to rotate it further, but you have to know the state. And for this we trained an additional estimator here called Deep Differentiable Proposal Particle Filter. And what you see on the right is the estimate this filter is outputting from the sequence and time series of the position and torque sensors sensing it gets from the hand. So it's quite stable. It starts with, in the beginning, it starts with an uncertain state, and wait a moment. So it starts with uncertainty, and then it very quickly converges to the quite sharp state. And if you have this, you can do goal-oriented reorientation. So we can now perform rotating objects in this case, the cube, in all possible 24 different orientations. You can orient the cube. And it works almost 100%. Again, no vision involved, all purely tactile. That's always important to know. And this is a simple example to show how robust it is. So here, the robot is looking at the target cube, and then, here, it's looking at the target cube, and it's then reorienting its own cube purely tactile. And it works for very long sequences without ever looking at the cube in the hand. It's all tracked from the initially it's told a state, and from that on it's tracked via this estimator we've trained in simulation. And so this was ×8, but we can also do it quite quickly, and this is ×1. So this is what we just will show at the humanoid conference paper. So the hand is really fast, and we have the center wheel under control quite well. So we can do this in-hand manipulation. Superhuman. I have one PhD student who is faster than the hand, so that's why I have to put it into. I cannot write it very boldly. So this is only to show the simulation. We use ISAXim, but the important thing is to model the context precisely, because if you are not using vision, you never get the global state of the cube of the object. You have to all errors would add up. So you especially have to do a very precise torsional friction simulation, and we found a way to do it in ISAXim, so that's why we achieved this high success rate in the end. And what we just have shown on at the IROS conference, we can now also handle more complex objects which are non-convex, and we have a single policy which can handle different kind of objects. We simply have to put in as another input the 3D shape of the object, and then again purely tactile we do the reorientation, and it works with for the test and training objects with a success rate of more than 90% of reorienting it in any of the 24 possible 90 degrees orientations. And you can even do out of distribution objects, not with that high success rate, because here in the end the resolution of the torque sensing is not enough, so you need some spatially resolved activity to do these more complex tasks, more detailed objects. Okay, and this is an example of combining grasping and in-hand manipulation. So it grasps the objects and can in-hand manipulate even these quite large objects, and he finds often ways which are different from what I would expect. So we tried to make it very hard, and it always found a way to get around the hard reorientation part. And it works also very robust for these quite large objects where the simple strategies are not working anymore. Okay, and if you want to go even in more detail of manipulation, so more fine manipulation, then so things like the human are doing, which is amazing. You can do this task completely blind, grasping into the box and taking out a little tiny object, reorient it and put it into the here in the board. And key for this is especially highly resolved tactile skin. So if you remove the tactile sensing, so this famous experiment from Johansson's, then you get really bad as a human. So it's the tactility which is important, and the spatially resolved one. So that's the reason we added a tactile skin, and it's really a skin, so you can simply glue it on the structure, and that's it. Then you have, in this case, 4x4 taxar resolution, and it has a sample rate of 750 Hertz, and we will now show two example manipulations, rolling a small marble and rolling a bolt in different orientations. And again, we do everything training and simulation. So we built a very precise model of the skin in the simulator, which is precise enough to directly feed the policy then with a real sensor signal, and still it can perform the task then in reality. Only a word about the skin. So here you see the resolution. It's holding a bolt, and if you rotate the bolt, then the taxal image is also rotating. And this is a paper which is a little bit older, so we used the high sample rate of the sensor to identify materials simply by sweeping the finger over the material. And we reached, in the end, superhuman performance, 36 materials. We did a psychophysical study to compare how well does the human identify these materials if only touch is allowed, and how well does the robot the thing, and the human is only half as good. So in a sense, tactility is solved. We are even more sensitive than the human. There's some problem with the sensors. They are not robust enough for the real world application, so it works in the lab but not in the real world. Okay, and this is now what we can do. This trained policies using our simulation of the hand, fine manipulation of a little marble. So here rotating it in a circle, and here in a square, so we can position the marble with a precision which is even higher than the resolution of the skin, because it's super taxal resolution in a sense, because we not only use an on-off signal, but the 8-bit signal of the skin can be used to precisely locate the object down better than the basic resolution of the skin. And this is another example where we rotate a bolt, and it's one policy which can rotate the bolt in different orientations. It simply feels how the bolt is lying in the fingers, and then it rotates perpendicular to the felt orientation. All trained in simulation and directly deployed to the real system. And this is here an example of combining the in-hand manipulation with motion planning to achieve a task. So here we have to sort and reorient the cubes in a way that we build a tower which is writing the initials of our two hosting institutions, TOM and DLR. And this means we are really confident and have a really robust in-hand manipulation skill now, that can be used in an overall more complex task. So the conclusions, in our experience, and autonomous learning is key in dexterous manipulation with multi-fingered hands. You cannot do it with imitation learning. All the forces and such stuff, this has to be experienced by then, and you cannot extract it from a video out of the internet. When you see someone manipulate something, you have to feel it, and you need the system understand what it's doing by experiencing it in the simulation. So we are very sure, and this also shows the experience we made. And we think we are ready for deployment in the real world. In a sense, this in-hand manipulation is exactly what industry is telling us. They need basic tasks, take something out of a box, reorient it, and put it into the automation system. That's where a lot of people are working in industrial manufacturing. And to be ready for deployment, this means we have now the AI, and what's missing is a robust hardware. So the hardware here is not robust for the real world. But robust, we are working on this, so we have now fingers available, which we will integrate in a full hand, which can really handle hard impacts as well, and they are as dexterous and as strong as the hand we have here. But this is, we will announce, it will be commercialized, and it will be announced sometime next year. But, so, all these successes are nice, and I think that we made quite some progress, but still we are in the stone age of learning methods. If you think of this in-hand manipulation, which we can train in 5 hours on one GPU, that sounds really efficient, but compared to the human, that's nothing. So if you think of the number of rollouts we generate in these 5 hours on the GPU, if a child has to do this, it would have to do 8 hours a day, rotate cubes for 10 years to have the same number of rollouts. So we are catastrophic sample inefficient as with our learning algorithms, and that's where the really interesting research stuff, in our opinion, will happen. How can we make it more sample efficient, and then we can learn in the real world, we can learn in way more complex simulators which can be built on VM simulations and so on. So there's a lot to do to make it even better. So this is the team which is working on the AI part at the IDEX lab. And you can see all the things I've shown in the video live upstairs. We have it here, and it's not only working in the video, it's working live and robustly, I hope still, robustly here upstairs in the second floor. So, thank you.
Okay, so I'm excited to announce that we are continuing these sessions in the afternoon. Our first speaker in the afternoon is Dr. Hermans, who is a professor in University of Utah and also a researcher in NVIDIA. And today he will talk about what's the right recipe of learning multi-figure manipulation.
Okay, thank you. Is this too loud? Or is it okay? Okay, that's good. Yeah, so I'm not going to talk about what this video is, but I just wanted to show it because it's fun. So, as the title says, right, I'm going to talk about multi-figure manipulation. Okay? And that's the term I typically use because I think about multi-fingered hands and what they have to offer us in thinking about building robots. And the first thing is stability. Compared to, say, two-fingered grippers, if we want to lift things like this spear and have our robots run around with spears, right, there's a large moment at the end of that that you want to be able to resist internally with the hand instead of allowing it to rotate in something like a simple gripper. But at the same time, they offer versatility in terms of being able to generate a wide variety of grasp, even on the same object, or to work on a variety of objects. And with that versatility also comes dexterity. So the ability to hold things like this stone, and you might ask, what is dexterity? I think that's a great question that we can argue about. I don't have a really formal definition, but generally I take it to mean the ability to, when I'm talking about multi-fingered hands, the ability to repose an object relative to something like the palm, some fixed part of the hand, without using the arm necessarily. If you want to debate with that, talk to Nima here. On Monday, he was making us argue about this while Dieter's just trying to enjoy his sauerbraten. And, so I defer all arguments about dexterity to Nima. Okay. So today I want to talk about different approaches we've taken over the years to dexterous multi-finger manipulation and thinking about how we want to do it. And so here's a paper from 2015, so nearly 10 years ago, where we're doing reinforcement learning in the real world using tactile sensing on a multi-fingered hand, although we're only using 2 of the fingers. There's no neural networks here. This is all being done in a Hilbert space using kernel methods. Work primarily done by Hecker van Hof, who's now faculty at the University of Amsterdam. And we see, after only a handful of trials, we start to see behavior where this robot can move this cylinder from one side of its workspace to the other. And we see that in a second, it can transfer to novel objects. And this is really key to most of the research I do. How do I get skills that I can generalize to novel objects, where ideally I only see them from partial view information. I don't have any sort of explicit models of them a priori. And I think building skills that are versatile across many objects will allow us to then have robots that can generalize in interesting ways by sequencing these with planning and other techniques. And so that's one of the first lessons that I learned, right? I did this during my postdoc at TU Darmstadt, and then, a year later, I moved to Utah, and we did this thing called motion planning, and we were able to get very skillful motions, moving objects to new poses. In all the experiments we did for this paper, the robot never once dropped the object for our method. Importantly, we're not making and breaking contact. And what we found after this paper is that's really where things got more difficult, right? I expected this to fail, and that we'd have to use tactile feedback to improve it. But Bäuml, my then student, who's now also a colleague at NVIDIA, is a very clever motion planning expert and figured out how to make this work, right? And we could make it work for a variety of grasps, but importantly, all of these grasps were with the fingertips, right? And this motivated us to really look at how can we both acquire the grasp and do the in-hand manipulation and focus on having, specifically grasp with the fingertips that are precise. And around that time, we also started looking at doing large-scale data generation and simulation. So we could take advantage of neural networks. Right? And we were motivated for a very specific reason. That was, we wanted to make sense of visual data. And after my PhD in a vision lab where I spent most of my time handcrafting features and trying to make them work, I was really excited to not do that anymore and let neural networks figure that part out for us, right? But we didn't want to throw away all the knowledge we had. We wanted to leverage things like motion planning and really let the learner figure out the stuff we didn't do a good job at and not have to figure out the stuff we know how to do. And that motivated the following approach that we developed over a number of papers. And it works something like this. We first train some sort of generator network. So here it's something like a mixture density network. So we can sample grasps conditioned on the sensor input, right? We train this as our neural network. We sample these grasp configurations. And in this work and most of the work, we did a grasp configuration as a pre-shape and a palm pose. And then we're going to close the hand using some sort of controller that that works relatively similarly in the simulator and the real world, so we can get zero-shot transfer. Okay. What we found is doing this sampling kind of regression-based method doesn't get very precise predictions relative to the training data. And so what we do instead is we initialize, using this grasp configuration, an optimization, where that optimization's cost function, which we can think of as a form of probabilistic inference, is a classifier that's also a neural network trained to predict success of grasping, right? So we can get these labels of success for free from the training data set in the simulator. We simply have the robot pick it up. If it's successful, positive example. If it doesn't, it's a negative example. Then at deployment, we can optimize over the grasp configuration theta. And importantly, we can add constraints. So here, I'm just showing, bound constraints on my joint limits. But we can also add things like reachability constraints using the forward kinematics of the robot. And I'll show in a second more complicated extensions of this. But importantly, right, things like constraints, forward kinematics, we have models for those. We've known how to figure out and use those and efficiently compute gradients through them for decades. We should use them. I don't need to learn a policy to do reaching in space. So here's just some examples of graphs that we generated using this approach, showing that for novel objects we can get a diversity of grasp. Here we're kind of highlighting overhead and side grasp. Not all of these are precision grasp. Not every work that we focus on that. Here are examples of both precision and power grasp. We looked at having ways to actually condition on which one you wanted, and you could leverage. You could specify if you wanted them, or if you simply said, give me the most robust grasp, it would automatically optimize for one that was a power grasp, knowing that that had a higher success of not dropping the object, which was a nice result we found in this. Later, we examined learning object reconstruction, similar to what was shown before, but here we're learning it as a signed distance function, so that we can actually use that as another constraint in our optimization. So we have this partial view of the object, we reconstruct it as an SDF. We're showing a mesh here, but we don't actually have to generate that mesh at runtime. We can directly query the signed distance field. And then we can use that in two ways in our optimization-based inference. So the first is as a collision avoidance for the palm and the robot arm while reaching and while maintaining that pose. But then also we can specify contact between the fingertips and the surface of the object. So now we can specify that we want this fingertip grasp. And in doing so, we also leverage tactile sensing because we know this reconstruction for novel objects is never going to be 100% accurate. So if the robot's reaching to an unobserved part of the object, if it detects contact sooner than expected, we can stop the fingers. If it doesn't detect contact when expected, we can continue to move in the direction we think the object is using the gradient of the SDF until we detect contact and stop. Then once we've stopped, we can reevaluate the terminal grasp that we've come to using the same classifier we've trained, or now an in-contact classifier as opposed to a pre-shape classifier. And if, say, the probability of success is low, you could have the robot not try something, right? So this is another, I think, strength of these inference-based approaches, is if we calibrate our probabilities to be somewhat accurate to the real world, we can have measures of confidence and uncertainty that we can use in downstream planning tasks. I'm realizing now I'm also going quite fast, so there might be a lot of time for questions, which is fun. Okay. Here's another example that we built on in this, where we're doing constrained pick and place. So here we're jointly planning for both the grasp and a target placement. And the important thing to note here is that if you want to, here the robot's trying to place this object in a far corner, even if, say, the top grasp is maybe the most reliable, it needs to use a side grasp to be able to reach that. Right? And then working in clutter, this becomes even more constrained, right? That we need to, let me play that again. Right. So here we're reasoning about collisions with the environment, jointly placing and grasping. And again, most of these things are model-based other than our grasp prediction. Okay. So this framework allows us to add all kinds of prior knowledge from our models. Here it is in the real world. So here, picking out of clutter and placing into clutter. We have a fairly conservative approach here where we look at the entire swept volume of this reflex hand for collision avoidance, so the objects can't be too tight. I think we could overcome that pretty easily by improving kind of the pre-shape configurations. But again, we solve for pick and place, and then we solve the motion plan to go between the two as a separate optimization following the primary one. Okay. So here's kind of an overview of this approach. Right? I'm going to characterize it this way to then compare it to a few alternatives that we've looked at as well. So we take our camera image, we perform some form of object segmentation to get an object-centric representation, an image, a point cloud. We then use this optimization-based inference with constraints to generate a grasp configuration. We then run a motion planner to move to the pre-shape, execute a trajectory optimization to get in contact grasp, execute. Okay. So some strengths of this approach, right? The number one thing we cared about, we can do. We scale novel objects if we train our visual perception across many objects in simulation. We scale novel environments because we can leverage off-the-shelf collision avoidance in our optimization to ensure that we don't run into things in planning the grasp and the motion to the grasp. We get a diversity of grasp. So one important thing that we saw that was lacking in a lot of regression-based approaches when we started this was that they would kind of average out and only give you a single grasp per object. And we really wanted to capture the full diversity of potential grasp for an object so we could delay selecting which grasp we wanted to downstream reasoning. So like the video I showed at the very beginning where we're sequencing multiple actions, certain grasps are going to be preferred over others. And I think this is the negative one. Nope. Another positive. We can integrate tactile information into it. But the next one will be negative, right? So there's got to be a catch. This whole thing's really slow, right? Solving this big optimization with all these models is very slow. So that's annoying. First, just because you have to wait for the robot, but more importantly, if you want to actually have feedback, like throw this into like an MPC style scheme, it's going to be very difficult to do that. And so this motivated us to look at alternative strategies for trying to get fast reactive grasping. And our current approach to that was presented at the conference this week. Here, we're just showing the results. Carl, my collaborator, is presenting the robot with objects. It messed. Oh well, I'll try again. This time it worked. It's going to continually do this, just picking and dropping objects. To do this, we leverage many of the things we've used before. Perfect timing, Tyler. I'm showing your work. We're doing large-scale training and simulation. Here we train an RL policy from privileged state information in the simulator to work across a variety of objects. We then distill this into a policy that can use point cloud information alone, or depth images, to then work in the real world and transfer zero shot, right? And I think we're really focused on high throughput, reactive control here. We have this policy running at 10 hertz. Underneath the hood, there's these things called geometric fabrics, helping things be safe and not run into everything. There's a lot other tricks that we had to do to get this to really scale and train in an efficient way. And If you have questions about that, we can definitely talk about them offline, but more importantly, you should talk to Tyler, who just walked in, and Martin, who's sitting here, who are the students who kind of led this work. And so we're fast now, right? This is awesome. We've solved our problem from before, except we've lost almost everything I just talked about, right? We can generalize across objects, but our graphs aren't that diverse. Like, while they look nice fluid motions, they're kind of all these power graphs just kind of grasping around these objects. We can't generalize across environments at all, right? I have no idea how to efficiently train a policy that can leverage collision avoidance in any sort of constrained configuration like we can solve with motion planning. And so that left us wondering, how can we get this fast reactivity, but maybe get some of the benefits of our previous work? And I'll say now we don't have a complete answer, but we have a sketch of an answer, and I thought a workshop would be a fun place to kind of tell you about our sketch. Okay. And to contrast that other model I showed, right, here's our policy, right? We have a camera image now, we don't require segmentation, we also have the robot state as we did before, and then we have this policy that we're just playing out through a feedback loop. Oh, there you go, yeah? So here's the one from before, here's the one now, okay? They're slightly different, right? This one's a little bit more uniform. An alternative that's very popular, in fact, Tyler had a different paper here that I was not a part of, showing a very similar approach to this, where instead of using that optimization, we can generate many graphs from our generator, evaluate them, and say, look at the top one, and then plan to that. Okay? If it has a high confidence, we can execute it, it might work. This is a popular approach, they're not the only ones to use it. Jens is here, he's done a similar approach before. But if you look at works like this, we find, and some of our own, so I'm not gonna be hurting anyone here, there's a number of caveats we often put in these papers, right? If the robot moved to the pre-shape but failed to lift the object, we label this attempt as unsuccessful. Okay, that makes sense. If motion generation fails, we discard the trial as the failure is not due to the grasp planner itself. Okay, yes, when we're doing comparisons, apples to apples of our grasp planners, that's helpful, but as a roboticist, I want my robot to pick stuff up, and I don't want to blame the motion planning community for not solving the problem. I should take responsibility and solve it myself, right? We define our success rate as a percentage of success grasp out of success plan, and we define overall success rate as a percentage of success grasp out of the 50 trials. Okay, that's a confusing sentence, but if we look at the results, oh yeah, we get, 86, 77%, sorry, yeah. And if we take into account motion planning, we drop 20% success rates, right? So we should not be ignoring motion planning in our grasp evaluations. Okay. Other people said other things, okay, I'm not gonna, main thing is, this is a big problem. We shouldn't avoid it. Okay. So here's what we're going to propose. It's a very minor change to this framework. We're going to do motion planning before evaluation of our trajectories, or of the grasp. So what does this mean? We use our generator, and then we're going to plan to all of those grasps, and evaluate where the motion planner ends up, not where we told it to go. Doesn't seem that surprising. Why haven't people done this before? Well, the motion planning bit of this is often the most expensive computation, right? You're solving some motion planner. And this is where our NVIDIA affiliations come in. And we can do this on a GPU. We can do now vectorized, fast, parallel motion planning using our geometric fabrics and evaluate something like 500 grasp trajectories in parallel very quickly. And so we can do this. Right, and so here's a quote from from Bäuml, who did that in-hand manipulation work. His different motion planner than the one we're using, right? He can solve over 7,000 queries with an IK solver in 20 milliseconds. Okay? So we can do motion planning now. Okay. Ignore that. Okay. So let's characterize each of these kind of around a few properties. So we have our policy-based approach. It's very fast inference, but we can't generalize to multiple environments. But it always generates something. It's always going to try something. which we think is nice. Right? Our optimization-based approach is not fast. It works in multiple environments. It generally generates something, but it also gets stuck in local minima occasionally, so we'll say that's a no. Regression-based, also fast, also multiple environments, but doesn't generate always. It fails a lot, right? We saw that 20% failure gap. And so this, as you want in any of these tables we set up as academics to trick people into thinking we're clever, right? Everything works for this new approach. And in fact, what we can do beyond this is we can make predictions about the object pose using an object pose detector that we train in parallel. This is something we also did in the policy-based approach. And we can use that now to feed back in a feedback loop to replan if we need to, if the object fails to be grasped. And then we can also use that to predict, say, if the object shifted during grasping, we can update our placement plan to account for that shift online, as opposed to what we were doing before, where we were just jointly planning the pick in place with our inference-based procedure. So we're training this right now in a cluster with a bunch of objects. These are the same objects we used for the Dexterous work, the policy work I was showing before. Here's some example grasp in simulation. We see we're getting diversity, grasping upside down and close to the table, grasping different objects. And so here's a video to kind of show some of the predictions. So we're showing the object pose here, and then we're visualizing predicted grasp poses. And you see that this generator is telling the robot to put its hand inside the object, which is not a good grasp. But because we run the motion planner with collision avoidance, it approaches this grasp it best can, and we get a number of grasps that are close to the object surface and shaped in a way that if we were to execute them with our controller are going to work. And so this is exactly this switching of the pipeline approach that'll happen. I'm hoping this is like a very early model that we can do better, right? But when we get good grasp, they're not all going to be inside the object. But this is really just to showcase this idea. Here's a couple of grasp just to show this is working in practice, even if we've yet to really scale it up. Martin's shaky cam cinematography at work here. Okay. Yeah, and I mean this is pretty much the end, so I think I can stop there and take questions.
Okay, any questions?
Yeah.
Yeah, if you're running this in an NPC style, what's the full time it takes to execute?
I don't have an answer yet. We haven't fully done it, but I don't know. Throughput's pretty fast. It's just a little more than a standard neural network 4 pass. Yeah.
So why are we treating grasping as a discrete problem, generating discrete samples instead of generating a distribution around something?
So I mean, we are learning a distribution.
Yeah.
And originally
then we sample from it. Why not learn some energy or something that tells us that?
Well, I think that's just slow to do that inference, right? Yeah. But you could always iteratively resample as a form of optimization over the continuous plan. So I think you definitely do that. But I think that's a great point. I agree. We should not treat it as a discrete problem. Yeah, David.
As I understand it, you weren't using tactile sensing in the last piece of work. So why did you keep the biotacts on the?
So we do use them to detect when we make contact, and then we stop on contact, and then we kind of clamp down and apply more force using the biotacts. Yeah. Anything else for Roberto?
Okay, our next speaker would be Roberto Calandra, who is a professor in TU Dresden, and he will today talk about the importance of touch sensing for Dexterous manipulation.
All right. Good morning, good afternoon, everyone. It's a great pleasure to be here today. And today I'm going to have a very fast and very controversial topic, which is going to be the importance of touch sensing. And what I want you to get out of the end of this talk is that I very strongly believe and will sort of push you to this idea that we do need touch sensing. And although many people might disagree that we might be able to solve everything with vision, I very strongly believe that they are wrong. And time will tell. So if we look at the way that humans do manipulation, you have already seen many of these videos like this today. Humans are pretty spectacular. We can do extremely dexterous manipulation almost effortlessly. And on the other hand, if we compare to where we are now today in robotics manipulation, we are very, very far away. Now, one aspect that I think is important is essentially touch. And proof of the importance of touch comes from the very fundamental work of Ronald Johansson, who basically, in the past decades, have been studying how humans use touch. And this is a video where they anesthetize the sense of touch of humans while maintaining their motor control capability. And suddenly, a task that was very easy, like lighting a match, becomes extremely hard. It takes much longer. And this is because this human, and all of us in our everyday life, we actually use touch. And this was already shown before also from Professor. Now, the type of tactile sensors that I'll be talking today mostly is so-called vision-based tactile sensors. This is a technology that was originally invented in the 1960s, then was rediscovered in the 1980s, then it was reinvented again multiple times throughout the last few decades. But in the most modern interpretation, they were basically rediscovered by Ted Edelson at MIT around 2009. And the fundamental idea of vision-based tactile sensor is very simple, and it's the idea that we have an elastomer, effectively a piece of silicon up there, and this piece of silicon will be touching things, and we will be shining some sort of structured light onto this elastomer, and then record how this light is projected back into a camera. And whenever this elastomer is entering touch with something, this will create changes in shadows and color cues of how the light is reflected back, and this will be recorded by a camera. Now, over the years, we've been working on many different types of tactile sensors, but probably the most famous one that you might know is Digit. Digit was designed and open sourced in 2020 with the idea that we want to build a tactile sensor which is mass producible and can be easily and cheaply manufactured and sold. And if you have a 3D printer at home, you can actually 3D print it with a little bit of knowledge about mechanics and silicon casting. And the idea was not to have the best possible tactile sensor we can make, but to make something that is democratizing touch, in the sense that it makes it easy to use. And these are the type of readings that you get off of your tactile sensor. So here on the left you have a piece of Velcro, and you can identify, you can see below the individual teeth of the Velcro, down to a resolution between 20 to 50 micron, depending from the quality of the gel that you use. The gel that is commercially sold is much worse than that, if you have used it in the past. Now, an unfair comparison to biotech is that, which was the leading competing sensor at the time, is that both of them are possible to be mounted on multi-finger hand, but the Digit has about 3 orders of magnitude higher resolution, while being about 3 orders of magnitude cheaper to manufacture. And of course, it's also open source, so you can actually go there, you can reproduce it. And we know of at least 20 universities that reproduced a Digit and built it in-house, but we also partnered with a company called GelSite Inc., where we basically give them then the right to manufacture them. And over the last couple of years, they've sold over several thousands of these sensors around the world, making it probably the most widespread sensor in the robotic community today. In addition to the hardware, we also developed a fast simulator for Digit with the idea that we want to be able to simulate touch at hundreds of frames per second. And we can basically tune this simulator to be fairly accurate to reality of this sensor, and then we can use it in sim to real. And we have experiment in this paper, so we show that we can actually use and transfer model learning simulation to real world. Now, Digit has, in my opinion, many important limitations, and over the time, we've been trying to tackle some of these limitations. From the fact that the sampling rate of the sensor is relatively slow, it's only 60 Hertz. Human fingers can sense vibrations at much higher frequency, 500 consciously, 9 kilohertz unconsciously. The fact that each one of these Digit sensors generates quite a substantial amount of data bandwidth, and in the moment when you already have 4 of these sensors in a single USB 2, you basically will saturate the bandwidth. To the fact that the form factor of a Digit is relatively not super helpful if you want to do fine manipulation, because you only have a flat surface for contacting, and the depth of the sensor is about 2.5 centimeters, so they are relatively thick in thickness. And finally, the only type of sensing modality that they provide you is basically the, this geometrical deformation of the silicon. Now, over the years, we've developed also many other sensors that try to tackle these limitations. The OmniTac was an early prototype of an omnidirectional tactile sensor that was using 5 different cameras. This year, we published the EVTAC together with collaborators at Darmstadt, where we replaced a fixed camera with an event-based camera, thus enabling us to go up to 1 kilohertz in terms of sampling frequency and reduce the bandwidth, because instead of having to send signals all the time, we can selectively send signals only when something is happening. So along a typical manipulation trajectory, we could go down to about 2% of bandwidth usage, which means that now we can, in principle, connect hundreds of sensors in parallel. Another sensor that we developed is Pinky, which is meant to be a miniaturized sensor mostly focused for medical application, where we basically decouple the transducer from the actual interface, and we can therefore make it only 1.5 centimeters in diameter. And we also use it in conjunction with the AI model to show that we can actually touch prostate and be able to identify cancer tissue because they have different mechanical property compared to sort of same tissue. But all of this brings me to our most recent work that was open source just last week. And if you remember, Digit was motivated by trying to democratize touch. We want to build a sensor that is easy to build, that anybody can make. But this came with a lot of trade-off in terms of capability. And so the question that we instead try to answer now is, what is the possible best tactile sensor that technology allows us to build from years from now? And the answer to basically what is this best possible tactile sensor is Digit 360. Digit 360 is an omnidirectional vision-based tactile sensor which incorporates a lot of very novel sort of concepts and ideas. As you can see, it has a layered electronic sort of design where we possess, among other things, a neural network accelerator inside so that we can do local computations, we can perceive, we can compute representation, we can even control motors directly from the fingertip. We also have, very importantly, extremely high degree of multimodality, where we incorporate many different types of sensation, and virtually everything that your finger can perceive, Digit 360 can also perceive. And this work was done at Facebook. Michael Ambetta there was the leading designer of this sensor. And just to go through a little bit of the technical capabilities, here is a diagram that reports what in the literature is considered to be the normal spatial resolution for a human, which is roughly here. This is the resolution of a Digit. With the Digit 360, we're able to go down to about 7 micron, which is really, really small in terms of spatial resolution. And on the other side, in terms of normal forces resolution, we are basically going to also improve the performance by 1 or 2 order of magnitude compared to other sensors or a human. Similar numbers you will also have for shear forces, so it's roughly the same. Now, you might ask, why do we need such a resolution? Why do we need such a fine capability of measuring forces? And the answer is that I don't know, and I don't think that anybody knows, but this is exactly the questions that we want to ask. How much resolution do we need? Because this has a very big impact on the future development of tactile sensors. Because if we figure that we actually have benefit of being here, then maybe it's worth the cost of building tactile sensors like this. On the other hand, if we figure out, we can get away with 1 millimeter like humans do, then you can use basically cheaper technology and less technology. And a similar discussion is, which motivated the multimodality, is going on. We basically packed every possible sensing modality that we could think of inside this sensor, not because we know that this is useful, but because exactly we want to investigate and understand which one of these modalities we will need in the next generations of tactile sensors. And some of these modalities include geometries from vision base. We are able to measure pressure, dynamic pressure. We are able to measure audio of the contact. Sometimes you have small clues when you insert something, maybe it clicks, and we're able to collect this audio to know that something clicks. We are able to measure temperature and exchange of heat. We are able to measure, we have IMU inside, so we can also get IMU information if you have a sensor, maybe a hand that does not have proprioceptive information. We have Cypher's vibration, and we even have a gas sensor inside. So we can actually smell the air, and we can see if the material that we are touching is maybe coated in oil or coffee or whatever. And again, not all of these sensing modality might actually be useful for you, but maybe they are. And the answer is that I don't know which one is useful. And here is an example of the Digi360 being used to tap onto a bottle, and based on the response from the vibration, we are basically able to quickly see how much water there is actually inside the bottle, in the same way that a humans would. Similarly, the reason why we decided to include neural network acceleration on device is not because maybe everybody needs it right now, but if we look at the way that humans compute touch, we do have a peripheral neural system that actually takes care of building a lot of reflexes, where if you touch something that is hot, it's going to be your backbone that decides to retract the finger. This is even before the signal reaches your brain. And so what we want to do by having on-device compute is that we want to be able to eventually reduce compute representation on device, so that we don't need to transfer raw data and use a lot of bandwidth. But at the same time, we might want to eventually to delegate local control and decision making of the finger to the fingertip, so that, for example, if an object starts sleeping, we don't need to send the signals to our computer in the brain. We can directly know that the finger is going to push back and balance the object back. And this is what in humans is, for example, called independent finger control, and Felipe Vega has a beautiful paper on this in the context of robotics. Now, finally, in the last part of my talk, I wanted to very briefly argue of why do we need touch in modern robotics, and do we even need it really? And this is a funny sort of interactive game that I play with my students. These are two images. One of these images is a successful grasp. The other one is a grasp that is not successful. Can all the people that believe that this is a successful grasp on the left, raise your hand. 1, 2, 3, 4. Okay, 5. How many people think that the one on the right is successful? Yeah, a little bit more.
I think you're lying. I think they're both unsuccessful.
I think they're the same pictures.
The problem is exactly this, is that vision does not directly give us information about contact forces, and even imperceptible changes of 1 pixel actually makes the difference between being in contact and not being in contact. And the people on the right in this case are winning. This is where congrats, good job. This is where we actually have in contact and we're grasping the object stably, while on the left we don't even have contact with the object, but visually it's really, really hard to look at these cues. And this is just one of many examples of why I think we need touch. And in 2022, we published here at CoRL, funny things, look at the fingertip. Maybe you might recognize this guy in 2022. We basically published a paper where we show that we are able to rotate and manipulate all of these objects without the need for touch sensing at all. We can basically get away with proprioceptive information. And to us, it was very surprising. And to some degree, it was also a letdown because we were really thinking, okay, from proprioception, we cannot do this. And actually, it turns out that we can. But the year after, so last year, we actually published another paper. And once again, look who's here. All the people that last year would ask me, what's the thing on the fingertip of the, I don't know what you're talking about. And in this case, we actually benchmark and evaluate what are the differences in performance when trying to solve this task using only perception, against using also vision, and against also using touch. And the type of results that Halsey was there obtained in this really cool work is that actually including vision and touch performs better than only using perception, or only using vision and only using touch. And to me, this is a small hint, and that touch is actually useful and is helping us a robotician to get better performance. And in the rest of my next couple of slides, I will show another couple of examples of sort of small hints that we have in the literature about cases where touch actually helped. And this is not meant to be a comprehensive list. And so I apologize in advance, it's very biased, this work that I'm sort of familiar with or that I was part of. But if you have more evidence of really comparing and knowing that touch helps in a task, I would love if you can actually write to me and tell me, hey, you missed my paper, please add it, and I will add it to this list. And so another example that we have from early 2018 was actually learning to grasp. And in this case, what we were doing was to basically learn probability success. And in the moment when we use it to learn how to grasp objects that we've never seen before, from the same data, a model that was using both vision and touch had about 83% success rate, while a model that was only using vision to decide when to grasp had only about 57% success. So even in this case, we have proof that adding touch actually helped the performance. And touch alone was not sufficient to have this increase in performance, but it was always in conjunction with vision. In addition, specifically for grasping, the fact that we can also measure forces now with a tactile sensor is really cool because it also allows us to do gentle grasping. As a robots, very often we apply the maximum amount of force when grasping objects, but as a humans, this is not our favorite strategy. As a humans, we typically use the least amount of force necessary in order to be able to successfully grasp an object. And recently, actually just at this conference, there was another really cool paper from Jan Peters and colleagues, which also showed that in the case of inserting tasks, you basically get similar improvement in performance in the moment when you add vision and touch compared to only using vision. And similar results were available before using FTS or JTS, but in this case they actually use vision-based tactile sensors. So what I would like you to get out of this very brief second part of the talk is that do we really need touch in modern robotics? And my personal opinion is very much yes, we do need touch. We do already have a collection of evidence that is growing day by day that touch does improve in terms of increasing performance and also improves in being able to generalize to objects and environments and conditions that we have not seen at training time. To conclude, I would like to thank all the many collaborators I had over the year working with me, and in particular Mike Lambeda and Hosey. Mike was my partner in crime at Facebook when it comes to building tactile sensor, and Hosey has been an amazing student of Jitendra to work on manipulation. This is my current group at U Dresden, or at least a slice of them. This is our wanted robot. And we are also hiring postdocs, PhD student, and lab manager, if you are interested. This is the beautiful city of Dresden. And just two more communications. We do have, we are very lucky because we have been proposing and has been accepted the second workshop on touch processing at NeurIPS this year. So if you're planning to go to NeurIPS in Vancouver, please pass by. This is going to be, another really, really excellent workshop with amazing speakers. And we are also planning to organize a second edition of the Touch Sensing and Processing Summer School in 2025. We are already put up the website without, all the information, but it will officially be announced later, probably in December. So, thank you very much for your time, and I think I'm over time. So
let's have one question.
So wonderful presentation. Thank you very much. And I fully agree that we need touch, right? I mean, I think, beyond question. I want to make one comment, and that's on the Johansson video.
Yes.
That everybody uses to argue that we need touch.
Yes.
The first time I saw that, I had the opposite reaction. This woman has never ever done anything without touch. And it takes her 24 seconds to come up with a policy that works without touch, right? So to me, that video actually shows the opposite.
I don't think it shows either of them.
I agree with that too.
Okay.
We can settle for that. We can settle for that immediately.
I think that what it shows is that a normal human uses touch as a part of their standard procedure of their policy. And the sort of caveat of this, which has not been proven, is that I believe that having touch at training time is what allows this person to adapt on the fly in 24 seconds.
100% agree.
Okay, perfect. Thank you very much.
And our next speaker would be Animesh. Animesh is an assistant professor in Georgia Tech, and he will today talk about facets of dexterity, simulation, RL, and imitation, which is the whole aspects of dexterity.
Another way around.
Yeah, that makes sense. Thank you.
Dexterity.
No, this is just plain stupidity.
It's the same letters.
Okay, I think the next 15 minutes will be slightly different in flavor from what we saw with Roberto's talk. Less about hardware, more about how to use hardware. And it's also probably, I'm hoping to make this a conversation. I'm not just only going to talk about hands, but actually give you a perspective of hopefully we can actually build better tools in computing, both algorithmically and just like infrastructure. So what do we want? Well, what we want is everything our hardware can do, we should be able to do algorithmically and do that zero shot. It's like everything, right? State of robot learning looks like this. Either you do RL or you do BC. There's not a lot in between. There's plus and minuses for this. For BC, we say let's collect some data. The problem is too many problems, too little data. We have moved to what I've termed this thing, sweatshop delay. This is what we are doing right now. Robot data is sweatshop delay. It's unethical to get started with, but that's all we have, right? So What BC does is we can basically do BC with supervised learning, but there's no evidence right now we have that we will be able to go through the hump of generalization. We did not do it in vision, we did not do it in AV, we did not do it in LLM with much more data. Why would now happen? And data is much more expensive to us, by the way. Now, of course, there are proponents of people who's like, oh, but we have simulation works very fast, well, is scale all you need? Well, it turns out not so much, right? Because when you run RL, the magic is you're basically doing, I think someone said that, maybe you said that. We did grad student dataset. It's just that now, instead of doing controller design, you're doing reward design. Right? And it's not very efficient. We do it one by one. The process is frustrating. Is there a different solution? This has led us to some work where, like, maybe we have been using BPO as this sort of like single tool to solve all problems without really thinking, can there be a better algorithm? And what would it take to get there? So one tool is differentiable simulation. Differentiable simulation, at least to people who do control or were doing control before they moved on to doing RL, would give them solace that this is basically bringing ILQG and DDP back. That is the algorithmic idea, except that the solver should be more information. If you are using simulation for PPO, you have that information, you're basically throwing it away. So let's talk about DiffSim first. DiffSim is basically a solver which can give you gradients through time. That is it. Turns out the frameworks have existed for a while. The question is, how do we actually use this framework for control? The first thing you need to do is implement this at scale. This is where our friends at NVIDIA helped. We implemented this in work so that this is GPU fast. So you're not like doing this on CPU, so you're not starting with a disadvantage. Now the next question basically is, what sort of algorithmic framework would we need to be both data efficient and wall clock time efficient? It's important to be wall clock time efficient. It doesn't matter because we are using simulator after all. So now if you have a simulator that can differentiate through time, what is the problem? Why not just use standard sort of, we have done this thing for a while. The problem is very simple. The same problem we had in RNNs like 10 years ago, gradient explosions. You cannot backrub through time with neural networks where these systems can be arbitrary long. So what is the solution? Well, the solution is not super hard. You backrub through time whenever you can. Otherwise, you do Monte Carlo. Monte Carlo is what you do with PPO anyways. So effectively, the solution looks like this. Your reward currently looks like reward plus some value, except that the reward that you compute for a rollout, you don't need to do estimation purely through Monte Carlo. You can actually backrub through that part of the trajectory. That is the short horizon rule. This effectively gives us two problems. It solves the problem of gradients being smooth, an algorithm being basically GPU parallelized. So you preserve the GPU parallelizability, and algorithmically, it's equally easy to understand. I would even argue one of the reasons why PPO is super successful is it's very easy to use now. So you give us an algorithm that is easy to use. Happy to chat more, but in the interest of time. So then we basically said, okay, what sort of problems can we solve? In terms of very easy examples to very high dimensional examples. High dimensional because that is exactly where PPO is very hard to make. What we find is something that surprised us. As the problem becomes harder, we can find not only better solutions, you do better and faster. The top thing is basically samples, and the bottom thing is wall clock time. Wall clock time matters because, well, graduate students are iterating on these things. And on a high dimensional problem in this particular case, the humanoid with muscles, we found that in about 1 hour you can actually solve this problem. And PPO, you can keep tuning it and you'll probably get there, but it'll take forever. Right? And implicitly, because the simulator is slightly better than say, the versions we have had in the past, the policies also did not look super weird to get started with. We are not doing something special here. I don't know what happened here. I remember first time when we had walking policies back in 2017, the first thing we said, this is not how humans walk. So because we are using gradient-based methods, implicitly this is sort of regularizing the system to not cheat, or not cheat as much. Okay, so let's say we have a system which can give simulation-based methods a mechanism to do policy learning. Now, but this is something that was good, but it was not really beating model-based, it's effectively model-based method, and it's not beating PPO all the time. So a lot of people said, why should we switch? You are basically peddling us your view of the world. So then it forced us to say, okay, there has to be a reason why this is better. Then we went back to understand what is the true problem. Well, the true problem is they're using differentiable simulators to solve problems of contact. Contact is exactly the problem where simulators are bad, so the gradients are not going to be good either. Can we do something about it? Well, I'm not getting into all of the details, but I'm giving you the intuition. The intuition is we are doing rollouts. We get to control how to stop rollouts. We are using it in a simulator. An easy intuition is stop the rollout when contact happens. So you can stop the rollout at points of contact. In locomotion, the rollout, at least at optimality, is a gate cycle. In manipulation, it will not be a gate cycle, but it's still known contact. Contacts are obviously known in simulation. So it's a minor change in algorithm. Now the horizon of rollout is adaptive. Algorithmically, it's the same idea, but horizon of rollouts is not fixed ahead of time. Turns out that's a major difference. This is what surprised me, and I truly mean surprised me. I did not expect this. Notice the x-axis. This is million. This is PPO. We said, I literally told my students, let's keep running PPO for a week. So you can keep running your best algorithm for all the time you need. You will never even get to the solution. So it's not only faster or crazy faster, like 3 orders of magnitude faster. PPO is just bad as optimization. Zeroth order methods are not going to find certain types of solutions that first order methods find. This is very important. We have just been using something that we had. Now we can actually do better. So it's better and faster, and of course it works on all sorts of problems you can think of. So walking, running, all sorts of things. I think we already have a system where you can put this on the real robot as well. I think that was also a workshop paper here. Now, why is this being presented here? Like, of course, it turns out. Why it is being presented here? Well, this now gives us the algorithmic framework to solve problems in Dexterous manipulation. This is an idea that I have had for a long time, that we should not be doing reward engineering. I don't believe in reward engineering. Reward should somehow be computed through other ways. One of the things that we thought was object-centric reward is a good idea. What needs to happen in the world is usually invariant to who does it. I'm left-handed, you might be right-handed. For us, opening the jar means the same thing. What it means is change in the environment is the same thing. That is the invariant. So understanding object trajectories is the definition of the task. Maybe we can get them from post-tracking. I think Jitendra and team beat me to it. They have a recent paper which does something like this. But I think I'm actually glad that you did, because at least we are converging in terms of ideas. So the kind of problems we're looking at is, okay, not just rigid objects, can we do interesting things like what we call operable objects. These are articulated objects where the root is not fixed. Algorithm is, oops, I don't know what happened here. Algorithmically, we are using the same framework that I just told you. The only thing is, this time around, I'm basically doing reference tracking. This is something that everyone in control knows. Except that the reference is only of certain part of the state space. The state space is object and robot. I only give the reference to you for the object. Operationally, this is not new. We do this in animation. This is exactly what is called sketching. You'll sketch the trajectory for only the torso or the head, and you want to find a dynamically feasible trajectory. This is basically the same problem, except the whole linkage is not connected. Right? So we started with something that is what I would call pedagogical, just to make sure that things are working, but the task is actually different. Instead of making the usual thing like do this, where everything works in PPO, we added stiffness. So now you actually only certain grasp would work, other grasp wouldn't work, which makes the problem hard in exploration. Turns out, even in very simple tasks like this, you can make PPO very easily flat. Just a very simple observation we found was, our current algorithms are good at opening things that are pre-loosened. If I close the water bottle tight enough, there is no algorithm right now that you have that can open this water bottle without cheating, meaning you actually have to provide a particular grasp or a particular solution. Effectively, you will need to cheat just to let the solution arrive at this thing. Like you can run PPO forever. It doesn't work. That is actually something that is unsettling. So we wanted the reference. Currently, we were looking at reference only of what you would call poses, but we wanted in this work the reference to actually be poses and forces. Because many of the tasks are actually force driven, right? The amount of force you apply wipes this, not like trajectories. This is exactly what Roberto was arguing. Force matters. Sometimes it's just the force. When you are tightening a bolt, you don't tighten it to a particular position, you tighten it to, 30 Newton meter torque. Right? So that happened, and then we were able to show that you can collect. So this is the algorithm we built. It solves it very fast, so you don't even see it. PPO cannot solve the exploration problem, so it just like flushes around. This is a method of, let me play it again, or I'll keep playing. This is a method where the initial grasp is provided as a solution. So it's like, it's being helped by the humans beforehand. So the exploration problem is solved by the human, and then you just solve the control. Okay. So far, I told you that we can have better algorithms. Differential simulation helps us solve the exploration problem in RL, and we can construct better solutions. Now we are all greedy. We want to solve everything all at once. We want image-based policies that are multitask and do everything all at once. Can we do this? Well, first of all, we can. So now you have a system to solve independent tasks. Think of your whole RL system to solve independent tasks. Now, this is something that we do already. If we want to do image-based policies, we do distillation. The only thing we said is distillation can be made much faster instead of just doing simple behavior cloning loss or the usual dagger loss. Dagger requires simulation in the loop. You can do critic guided loss. You were training RL anyway, so you had critics for free. Doing this basically results in solutions where you can now do BC better than BC. In the sense you're offline, so you're better than Dagger in the sense that you don't need simulation in the loop, so it's much faster. Some people ask me like, oh, but we can always do it. Well, this is an empirical thing. Running RTX requires L40. You cannot train on A100 or H200. But if I take that equation out, suddenly you can train on a very large data set on A100. This is sort of like operationally useful. So we showed that again you can solve these tasks with image-based policies now, with multiple hands. Of course, this is not shown in real, but at least the tasks are of object interaction of particular poses. So rotating a key, moving hands, rotating objects, of course. And then the same thing. Oops, I wanted to show you this. That this is an example where if you just did the standard sort of distillation with Dagger, which is the current mode, you actually never discover the right poses. Critic actually helps a lot. Like sequence of contacts, you never discover this. So you can only do short horizon problems where exploration is not a problem. Okay. I don't know how much time I have. I'll finish up in like 2 more minutes. Final question. So far I told you that you need the simulation. Now what I'm going to tell you is actually you can do even one better. If you have the simulator and you're using it for data generating anything, data generation anyways, why not do model-based RL by learning the models? What does a world model idea look like? Well, I have a robot that can learn the model. I'm using this to train my agents. I'm going to use that data to train the model itself. There was a recent paper by called TDMDC2 by Nicholas Hansen from Xiaolong's group. And it's actually pretty impressive. They were able to train a single model for multiple tasks and showed very good performance at scale. It is like an inkling of how foundation models for RL would look, not just DC. But there was one problem. It requires online planning, which makes actual computation very slow. Turns out one good thing is completely ignored. The problem with differentiable simulation was getting gradients correct was always hard because you're always trying to differentiate through hard things. When you do neural network models for simulators, you are basically computing smooth estimates. Turns out, when you are learning the model, we find that making a model accurate is not the point at all. The point is to make sure they are smooth. Because what we really care about is not really the model, the solution that you can construct with the model. With this simple intuition, we can construct an algorithm where you train with all the data you can find on any task, on all the simulators. Now they don't have to be differentiable to begin with, but your model is differentiable. Again, algorithm is still the same. It's just that this time around the model is not ground truth, but this learned model. And now you can train many policies. The policy training itself happens in like a matter of minutes actually, less than 10 minutes per task. This is again an impressive thing. For single task results, we get this number. This is the number, and this is the number that is using differentiable simulation. This is sort of like mind-bending. I'm using a world model to compute policies, and my policy is better than using ground truth. So, like, it's as if it's the same environment. If I had access to the environment, I'm not able to get this good. It's the fact that algorithm makes a very good assumption. Again, allows me to find a very good solution. It's an optimization system from a control perspective that is better. This is very useful. Now, because I was doing one task, I can do many tasks. Who's stopping me? So now, basically, the same model is better than TDMTC for multiple environments. And if I compare this with ground truth single task models, so specialist versus a generalist, the generalist is almost as good as specialist using the ground truth, and the generalist is completely offline. This is very important for us to think about how we might go towards this sort of like multitask image-based models. So it's much more scalable, it's pre-trained, completely offline, and matches single task experience. Yeah, so I think if there's one thing that I would like this room to step back is, we want to solve a very hard problem from control perspective, and it is requiring a lot of exploration. I don't believe we actually have the algorithms to do it. Even if my algorithms are not yet optimal, I believe we need to also work towards algorithms. It's not just somehow reward engineering problem. It's a problem of fundamentally writing good controllers for our systems. Differentiable simulators and ideas from LQG, are very good and should be improved on that. At the same time, differentiable simulators are also useful for data generation. We have done this for generating very good grasps. You can do state estimation with this. Things like you have images or videos, and then you can make sure that differentiable simulation plus differentiable rendering gives you very good, dynamically feasible, force-correct trajectories that you can use for BC. These are the main papers I talked about, particularly. Most of them are fairly new this year, but this is something that we've been working on for at least 3-4 years now. I'm thankful for the organizers to invite me here. Thank you for being a patient audience, and thank you for the privilege of attending.
And we will have just one question.
The PWM work is different than TDMTC. They both use the same differentiable model, right? The dynamics learning is identical, but
how you compute the policies.
right, exactly. So you have this adaptive horizon that looks at what then? That again is the same thing on the discontinuity of the dynamics model.
So I think in this case the model is not very discontinuous, so that you basically just stop at some point, like 32 or 64 steps, because that is where memory is.
I see.
Yeah.
So then how they differ?
Oh, TDMTC doing online planning, so it's not really policy learning, it's sort of like one instance computation of system, while this is policy. So at inference time you're running a policy, while TDMTC is the equivalent of running MPPI.
Right. Well, to be honest, they also have a policy, right? And they sample from the policy as well, but they also sample from MPPI, so they do both. Right?
Yes. But at test time, I think the main difference is in test time. Test time, they are doing inference time planning, and we are amortizing all of that planning in policy.
Okay. Now we are going to have the spotlight session again. And if you are presenting, your schedule is in our website, and then our website, you can scan the QR code to know the website.
Hi, I'm Hermans, and today I'll be presenting robot utility models, or RUMs for short, a framework for training focused and functional utility models that can be deployed in novel environments without any further data or fine-tuning. Here we show a RUM policy for object reorientation. To train RUMs, we collect a large, diverse, task-specific dataset of around 1,000 demonstrations from 40 environments. We can then fit a large behavior generation model on this data to predict a 7-dimensional action, giving us our RUM policy. Finally, these policies can be deployed in novel environments with no new data or fine-tuning. We test RUMs on 5 tasks, including object reorientation, door opening, tissue pickup, and bag pickup. We also add a multimodal LLM into our deployment loop to recover from failures. After a fixed time horizon, the robot sends a sequence of its observations into GPT-4o and asks it whether the task has been completed. In this case, grasping the teacher and picking it up. We found that simply doing this retrying, we're able to increase overall performance from 74.4 to 90%. Everything I presented today, including code, data, hardware, and models, has been open sourced on our website. And for more insights, please check out our paper. Thank you.
Scissorbolt, learning generalizables.
Hi, I'm João. Glad to share our work Scissorbolt here. Scissors are common tools in our daily life, often used for tasks like paper cutting, which shows the dexterity of our human beings. So in this project, we tackle the challenging task of generalizable paper cutting using scissors with only RGB observations. So we propose Scissorbolt, the system combining simulation, imitation learning, and sim to real. We first build the first paper cutting simulation, and we collect a large amount of demonstrations in a heuristic way. Finally, we distill it into a vision-based imitation learning policy, and we using some sim to real techniques to deploy it in the real world. So this task is really challenging because the paper features the continued deformation and changing topology during their interaction. So our policy can achieve robustness and generalizable across diverse curves, benefiting from the large amount of demonstrations we trained in the simulation. So our policy can also achieve generalization on diverse materials, which exhibit a range of properties like stiffness, bending, and stretching. So thank you for listening.
Hi everyone, today I'll be presenting OpenTeach, a versatile teleoperation system for robotic manipulation. This is a plug-and-play system which you can integrate it with any robot and you can teleoperate the robot using a MetaQuest 3. This has been written in such, the code base has been written in such a way that you can easily wrap out a new robot just by adding a new class, and you'll be able to use it to teleoperate, data collect, and learn policies with it. The idea behind it is to integrate any ability to integrate any camera sensors, tactile sensors, also like different robots which you want to teleoperate directly. Here, a person is trying to move his hands, and based on the hand tracking from MetaQuest 3, we are able to retarget these positions to the robot actions, and by creating a local frame for the wrist detection, we are able to move the arms as well. This works for bimanual as well as single arm things. Check out our website and attend our poster session to know more about it. Our code has been completely open sourced. Our VR applications has also been completely open sourced for the benefit of the community. Thank you.
Hi everyone, here we present our work. DRO-Graphs, a unified representation of robot and object interaction for cross-embodiment Dexterous grasping. So Dexterous grasping poses a challenge due to the precise interaction required between the robotic hand and the object. Both robot-centric and object-centric methods have their drawbacks. To overcome the limitation of both, we introduce DRO, an interaction-centric representation that captures the relationship between the robot and the object. DRO representation is a point-to-point distance matrix
between hand and object at grasp pose, implicitly encoding the grasp. At high level, our method takes point counts as input, predicts DRO representation, and derives joint values. We also introduce configuration invariant pre-training using contrastive learning method to match points across different hand configurations. In EXACT-Gene, our method generates diverse graphs and achieves an 87.53% success rate on unseen objects, much higher than baselines. And real-world experiments with the leap hand on 10 unseen objects showed an average success rate of 89%, further highlighting our method's effectiveness. And feel free to reach me out during the process section for further discussion for the poster 8, and thank you for your attention.
So I'm Abhinav. I'll be talking about using diffusion models to plan contact modes. So when we talk about contact modes, we're trying to figure out if different fingers are in contact with or resetting their contact with an object, like a screwdriver. Sorry, I don't know why this is black and this is white, but importantly, we're also trying to plan continuous trajectories between these different modes. So we have this discrete and this continuous problem. So our method, DIPS, plans these modes using trajectories sampled from a diffusion model, and we explicitly account for potential error that the diffusion models might make. Given a contact mode, we can then solve a trajectory optimization problem where different modes define different problems. So to do this search, we search over a tree of contact mode sequences. We sample trajectories from the diffusion, and then we refine this population of samples using likelihoods calculated from a discriminator, discarding bad samples. We use expectations over the cost of these trajectories to inform our search, and then we keep propagating down the tree in order to be able to plan our sequences. So here, this is a task where we're trying to slide a card, and our method on the left plans more reasonable contact sequences than the ones sampled from our training data distribution, as well as the diffusion policy baseline. We also do this on a screwdriver turning task where we can turn the screwdriver further than without planning. And then we also observe the same results in the real world, where we find that our method basically spends more time turning the screwdriver as opposed to resetting and regrasping with fingers that don't need to be reset. So for more questions, please come find me at our poster number 14.
Hi everyone, I'm Jane. I'm glad to present our work at Dexterous here. So Dexterous is a system that generates statistical data by manual Dexterous manipulation like humanoids. From a few source demos, we can generate a bunch of new demonstrations which can be used to train neural network policies. So Dexterous generates data for different large range of tasks, from this context-rich tasks like this threading and coffee making, to this long horizon tasks like this transporting. Also tasks that involve articulated object interaction, like this. And we also generate data for tasks with different bimanual coordination complexities, like this task with parallel execution, and the tasks that require two-arm coordination, and also the tasks that require a sequential execution of subtasks. So policy trained on Dexterous data trains shows very decent performance, and also find that with the same number of source demo, we generate 100, 500, 5,000 demos, and the policy performance keeps growing with more with a larger number of generated demos, and these are all based on the same source demos. So we also show how Dexterous can we also design a pipeline of generating real demonstrations with Dexterous. So from 4 source real demos, we generate 40 new demonstrations, and increase the success rate of this kind sorting task from 0% to 90%. So for actual details how we generate data and how to change policies, please come visit our poster at number 16. Thank you.
Hi everyone, I'm Roberto from Silvério University. Today I'm presenting our paper, Catch It, learning to catch in flight with mobile Dexterous hands. So catching is very important and interesting human skill, and it's very challenging for robots. because it requires agile whole body motion, extended spatial workspace, and rich object interaction. So we build the system in both simulator and real world. And because of the morphology, we decided to use reinforcement learning to discover the policy. And we propose a two-stage reinforcement learning framework, but well, no time for the details. Let's look at the results. The first stage, we train for tracking. Sorry about the typo. If you see it, it's only tracking the object without moving the fingers. It's just tracking objects. And in the next stage, after you get the tracking experience, you can do the actual catching. So now this time, the fingers are moving, and this can generalize to novel objects. So quantitatively, we show our method outperformed previous method in both efficiency and success rate. And here are real-world deployment. We tested on various shape of objects, including irregular shapes. And usually our mobile system can move both the all the chests, arm, and hands to catch the objects. And we show more success videos so that you can be more confident in our system. But of course, we have some failure case because there's always contact elasticity and the object might rebound off the surface. And that's it. Thank you.
So hi everyone. So I think I'm concluding the spotlight session. So in this work, we are analyzing the interplay and the role of vision and touch during insertion tasks. And we do that for both during training and during inference. In order to do that, we build a platform in which we can learn end-to-end policies directly trained on the real system. And we can also increase or decrease the task difficulty by just switching the insertion holes, where we can change the tolerances between the peg and the insertion hole, as well as changing the inclination angle. And for our policy optimization routine, we're using Dreamer, which processes the raw RGB images from an external camera as well as from a vision-based gel cell sensor. Our experiments during training reveal that vision-only policies struggle to learn on very tight insertion holes, while vision and tactile policies are always successful. And during evaluation, we evaluate our learned policies across a variety of different insertion holes with different task difficulty. And there we can see that with our vision tactile policies, we can retain high success rates, while vision-only policies tend to decrease in the success rate. And finally, we also carry out Shapley value analysis on the different influences on the action prediction from the different input modalities. But for that, we refer to our poster and happy to discuss further things. So thanks.
Manipulation skills like rolling dice, or pens, or kind of opening some lids. So of course, achieving this kind of dexterous task, dexterous manipulation for the very specific task itself is also very challenging. But still, this is far from what we expected at the very beginning. So we were in this task asking why is there such huge gap between the two. Of course, there are a lot of complexity associated with this problem. For example, the high-dimensional action spaces, the challenging dynamics, the under-actuation nature, the rich sleeping context dynamics, and also the hardware and sensor limitation and so on. But in this talk today, I would like to emphasize one specific aspect, which is the large and heterogeneous task space for a very general purpose dexterous manipulation. Of course, general purpose dexterous manipulation is not about just grasping, power grasping, or precise grasping. It's also about a lot of various of in-hand reorientation and also for some specific functional goals. Okay, so currently when we are considering dealing with this problem, no matter about choosing dexterous manipulation with reinforcement learning solution or using some more traditional model-based control strategy like MVC, we most of the time we have to design very task-specific reward and objectives. Right. For example, if you want to do this grasping, like I collaborated with Dr. Wang several years ago, like 1 year ago. So we're doing this kind of dexterous, universal dexterous grasping. There we have to develop very specific rewards so that the dexterous hand can really grasp it, reaching the object, grasping, and lift it to a certain height. Okay. So this is good for grasping, but still quite restricted. Okay. So we're asking this question: how to generalize to very diverse tasks? Okay. There's like a very interesting work from NVIDIA. This year's iClear, it's called Eureka, where they also want to tackle this generalized reward design thing so that they can design they can enable dexterous hands to perform various of tasks that's shown here. Okay, so they just like seek for large language models so that this foundation models can automatically design some interesting rewards for different dexterous manipulation tasks. But however, we're arguing that not all manipulations can be characterized by some sparse reward. Let's see some of the examples, right? Human trying to stir some stuff using tools or dusting the surface of some objects. All this kind of motion is not easily depictable by a single sparse reward or several sparse rewards, okay? So that's why we're asking, can we do a little bit more beyond this? So our key idea behind this presentation is that human object interaction trajectory, they actually provides a dense reference for dexterous hands. Okay, so if we can get access to diverse human motion data, then we could just use some dense tracking reward to learn diverse dexterous manipulation skills. Okay, so given some human interacting with some objects, some motion references, we just use some controller to really kind of transfer that skills to some dexterous hands. So this paradigm has been talked about for a lot of times, but I do think this at this moment when we talk about scaling up data, it has its own merits. Okay, so why? Because actually we do have ways to scale up the access of human object interaction data. Right? Recently, due to the progress in the computer vision community, right, we have witnessed a lot of efforts in trying to capture large-scale hand-object interaction data. So we have this dataset efforts back to 2022. We have developed this dataset called HY40 from my lab, and also we also have this kind of recent works from Professor Jitendra Malik's group doing like large-scale hand-object interaction capturing from images or videos. Okay, so this progress in the vision community gives us the opportunity to scale up human-object interaction data. So this also allows us to scalable considering how we can transfer these skills to dexterous hands. Of course, there are challenges here: the embodiment gap, the missing of the action information, and also the heterogeneous operation targets, and also the task space. Okay, so in order to tackle these challenges in this presentation, I would like to argue that we can maybe learn only motion planning from the human data and leave the rest to some general neural tracking controller. So instead of directly training some reinforcement learning strategy to give us some task reward, which will plan the movement as well as control the object movement, control the dynamics at the same time, we just turn to using this human motion data for the interaction planning. And then we will just use this interaction plan to decouple the semantics from the dynamics so that we can then develop some tracking controller to do the rest. So this gives one example for this kind of cross-embodiment tracking control paradigm. So given some maybe task description, which could be some language description, right here using a knife to drop, and you can use human motion data as some knowledge source to do what we call generative human motion planning. So here you will just plan the movement of the hand and also the object at the same time to make sure it is plausible and also kind of realistic. And then you will just leverage some what we call neural tracking controller to transfer that information to dexterous hands so that you can master that skill with dexterous hands. So I will just go through this paradigm in this talk. I will focus on 3 aspects, and for the first 2, I will briefly talk about our previous efforts and focusing on the last one. So first we'll capture some human object interaction data, then we can use this data to do the generative motion planning, and finally we can just like transfer this information to Dexterous hands using the tracking control scheme. Okay, for the first part, I will just briefly talk about this because we have already witnessed a lot of progress in the vision community. So in the last several years, we have a lot of efforts trying to capture hand-object interaction either in some like monocular videos or from a multi-view setup. So we have already seen like some high-quality data sets like TACO and also HY40 from my group. So with this kind of data, we have the knowledge source and also the test bed for us to test whether we can kind of transfer these skills to robot Dexterous hands in a scalable and generalizable manner. Okay, and also they provide a test bed for vision algorithms to test whether you can reliably recover interaction data from monocular videos. And once we get this data, the next question is this kind of generative human manipulation planning. The goal is to generate some kinematic motion references describing how hand manipulating objects. So again, we are kind of tackling this problem in the computer vision community using whatever generative models you like diffusion, VAE, GANs, but you can just use this kind of thing to capture the human motion data's distribution, and then using a supporting very versatile kind of task instructions to generate desired realistic human motions. And the final part is the most interesting and important thing is, once you get the human motion reference, how you can transfer those information to real Dexterous hands. So this part is more difficult and challenging because you have the complex contact dynamics and also the non-prehensile manipulation between the hands and objects. So here, the first idea we're thinking is maybe you can directly train some controller to track all kinds of human references in the simulator using your favorite reinforcement learning algorithm, plus the tracking reward. However, we found this problem to be super challenging because the object variation is huge, the contact dynamics is more complex than we expected. So we decided to decompose that into 3 steps. We first do motion retargeting to transfer the kinematic motion from human hand object to some Dexterous hands object. Of course, this is still the kinematic motion transfer. And then we do single trajectory tracking to solve some optimization problems so that you can convert the kinematic trajectory into some dynamic sequences. And finally, you just distill all this information into a single neural tracking controller. So this part, this part is also kind of echoing the recent data scaling law. Once you have huge amount of data, then you can just like train a super huge neural network, which can be super powerful. Similarly, we just treat this single trajectory tracking controller as some data generator to generate kind of tracking demonstrations. With these tracking demonstrations, we can just distill all the information into a huge neural tracking controller, which can generalize to a lot of different manipulation sequences. I will briefly talk about this single trajectory tracking and also the tracking controller in the next of the presentation. For the single trajectory tracking, so the problem is that given some human references as shown in the top left, we just want to physically control a Dexterous hands to kind of replicate that motion in the simulation environment. Of course, now we have to kind of consider the underlying dynamics, right? So we can not only do a single hand, but also multiple hands as shown here by manual cooperation. Of course, they don't really need to care about this cooperation thing because they have the semantic plots already from the human references. And we can also do more, okay? So this is published at this year's ECCV, okay? So I will talk a little bit more about this project. The task is that given some motion references describing a human hand manipulating an object, as shown on the left, we just want to output a dynamic sequence which can transfer in the skill to a robotic Dexterous hands as shown on the right. So here, we know given the contact dynamics and the sliding contacts, it's a pretty challenging problem. And previously, when people are dealing with this problem, either using reinforcement learning or trajectory optimization, they're mostly focusing on how can we improve the optimization paradigm, okay? So in this work, we are trying to ask the other question. So can we optimize the simulator design instead of just focusing on the optimization algorithm? Or more generally, how to optimize the simulation strategy for robot learning in general? Of course, when we think about the simulator itself, we need to consider the underlying dynamics, the underlying physical constraints. So, optimizing physical simulation on one hand, we probably want to relax some of the physical constraints to really make the objective of the kind of tracking task smoother. Okay, so we just want to maybe relax the contact constraints using some spring damper model, or relaxing the multi-rigid body constraints to release to make this optimization problem simpler. But on the other hand, if you do this kind of relaxation, the optimization problem is easier, but the sim-to-sim or sim-to-real transfer problem becomes much more challenging. So in this work, we want to answer this question: how to really benefit from the both. The answer is that you can just use both in a physics curriculum, okay? So this physics curriculum will kind of start from some low fidelity simulator, but which really supports very easy optimization and gradually making the fidelity higher and higher. Of course, for the high fidelity simulator, the optimization problem is challenging, but due to the physics curriculum, this curriculum learning scheme can help you to really solve this optimization problem in a much easier manner. Okay, so when fidelity increases, optimizability decreases, but the curriculum helps you to do the optimization better. With this kind of scheme, we can see that compared with both model-based and model-free optimization strategies, right? This MPC is model-based, and also for the control VAE, dgrasp, these are also model-free strategies. To see the success rate improvement is huge. And also some of the results as shown here, in the input human demonstration is noisy with penetration and missing contacts, while this kind of dynamic tracking results gives you much more pleasant results compared with the baselines, okay? And also, some additional thing. Now, notice this tracking really supports a wide range of tasks beyond just grasping and reorientation. And we also do some sort of sim-to-real study. Of course, here, the sim-to-real is not the focus of this work. We just do this sim-to-real in an open loop manner. We observe it's indeed a challenging problem in this case. No matter how work is in the simulator, there is still a huge gap between sim and real. Okay, but I think the optimization part is a general and transferable thing. And for the last thing is about once you have the single trajectory, how you can just distill all the information into a single controller to really allow a controller to track a wide range of references. Okay, so this is about tracking, learning a general tracking controller. So this is also a recent work from our lab. Now, you don't need to do single trajectory optimization, you just have a single policy. Given any arbitrary human references, you do this cross-embodiment tracking control on a wide range of tasks as shown here by this demonstration. Okay, so training a generalizable neural tracking controller requires the tracking controller to generalize to unseen novel trajectories with novel objects, and also at the same time being robust to the kind of noise, because you have the human reference, you have the retargeting, they all introduce more reference noises, okay? Now, what I just mentioned is you can just refer to the large-scale imitation to solve this problem, right? By doing single trajectory tracking optimization, you generate a lot of demonstrations for the tracking controller. You just now do a very large-scale imitation, you can distill everything into a general tracking controller. Of course, this seemingly simple paradigm has its own problems because the contact dynamics, single trajectory optimization is not always working. You have the very kind of biased tracking results from the single trajectory optimization results. It only succeeds on simple cases and fails on hard cases. If you now just distill all the simple cases into a tracking controller, your tracking controller will also be biased to very simple, maybe power grasp or prehensile kind of manipulations. Okay, so in order to really solve this issue, our proposal is to build the data flywheel. Okay, you have the demonstration and you do the kind of tracking controller. Once you get the tracking controller, you can use that to enlarge and diversify the demonstrations. So here, from left to right, I think it's pretty straightforward. You can use your favorite reinforcement learning with some imitation loss to solve this problem. But on the other hand side, it's more interesting. How can you leverage a tracking controller to improve the diversity of tracking demonstrations? On one hand, we can consider whether we can leverage the tracking controller to initiate the per trajectory tracking. For sure, you can do that. On the other hand, can we just explore the trajectory relations? Now we're just using this tracking controller to handle a wide range of tasks. Okay, so how can you leverage the trajectory relation to improve trajectory tracking? So we were proposing trying to learn some curriculum generator or homotopy path generator, which can convert a complex trajectory into a simpler one, so that you can first solve the simpler trajectory tracking problem and then get back to the complex one. Okay. I just omit a lot of details here, but this kind of general tracking controller also kind of performs pretty satisfactory compared with like very vanilla PPO with very sophisticated real-world designs. Okay. Yeah, here are some results. You have the retargeted kinematic references with a single tracking controller. Now you can do pretty reasonable job, and compared with very vanilla reinforcement learning. And yeah, here are more results. You have very challenging multi-stage tasks, trying to leave the shelf and doing some interesting motion. And you can also support all this kind of thing, while the baselines just struggle to really get the object started. Yeah, here are just more results in the simulator. And also we just do some real-world experiments again. So to compare that with PPO, yeah, we didn't really kind of manage to get the controller very smooth, but still from this simple demonstration, you already see now the tracking controller has the potential to transfer to the real-world environments. There are some more results. It's not a very kind of, the real world, for this kind of very big objects, it's not very easy, and because we are trying to use a single policy to handle all different kinds of challenges. Okay, so a summary for this across-embodiment tracking control scheme. We try to separate the planning and the control similar to the traditional paradigms, but so that we can learn the planning from human motion data and learn the control in the simulator. And this kind of partially separate the semantics from the dynamics, and both the neural controller and the planner, they can just benefit from the power of data. So a final conclusion for this talk, human videos are just ubiquitous to online containing huge amount of manipulation data, but how to really obtain high quality data and in what form is a very interesting question. And now we can learn to plan semantic manipulation from human data when the kind of motion diffusion or AIGC technology progresses, and how to really make it generalizable and plausible. And finally, this cross-embodiment tracking control paradigm is pretty kind of powerful, but how to really make the same to real working as expected is still a very challenging problem. I think this will just conclude my presentation today. Thank you.
So you showed a very nice idea of leveraging human trajectories to get this data inspiration, and then you put it in the simulator and then you get it to work. But then when you put in the robot, as you point out, there is a challenging sim-to-real gap. And why do you think, what's like the main thing we should address there to like maybe solve 80% of those challenges? Like what's the main one like that we should solve, and then it will be better?
I think solving the sim-to-real is for sure the most important part, but in this talk I was just pointing out another thing, which is about generalizable learning. Where does the data come from? I think these two problems are equally important if you want to have a general purpose dexterous manipulation system in the end. Right now, I fully acknowledge all the efforts about using maybe additional sensing, better hardwares, and also trying to make a single situation, single kind of task working really great. I think these are very important. But for the general purpose learning, I think that problem is very challenging as well, even in the simulation environment. The sim-to-real itself can, at some moment, also benefit from the human demonstrations from our experience. If you have very natural movement compared with weird reinforcement learning explored trajectories, it also gives us some kind of promise. Maybe you can do the sim-to-real better if you're really taking human knowledge into consideration.
Very impressive. You clearly said it's about kinematic trajectories. I was wondering if you have any thoughts on how to go beyond that. So, for instance, not to squeeze a tomato too hard. I guess it's going to be very difficult to get that from the human videos, but any thoughts on how you could get that in there?
Yeah, I think it depends. Firstly, I would say that getting the kinematic trajectory itself is probably not a very challenging problem after maybe several years. So we do witness very rapid progress in the vision community trying to make that problem more and more trackable. But I totally agree with you at this moment that it's not a solved problem already. So we're also thinking some alternative strategy. Maybe you just do the hand motion extracted from the videos, and then you can use the video as the vision input with maybe hands as the action, trying to do some sort of VRA stuff. Or you can consider trying to extract some additional information related to context and using that as some sparse planning signals for the task. That is also a very promising direction, I think.
Quick question, please. Yeah. So in this work, are you tracking just the object trajectory or also the hand and object? Do you have to tune how much you weight each of those?
It's kind of like a tracking both together because we want to also kind of inherit the information from the human hands. For sure, tracking both from noisy kinematic motion is not something very easy. So we have to maybe favor the object motion and also kind of trying to maybe weight the hand as the guidance. Properly.
Who is going to talk about data efficient learning of vision and touch for manipulation tasks? Please.
Thanks so much. We've come a long way in grasping and manipulation, but there are still challenges that we need to overcome to move robots from structured environments to unstructured environments and get them to accomplish tasks successfully, and have systems that are realistic, robust, and reliable. So ideally, we want them to be. We want to demonstrate a task to them like this, as we did in the Stephane project, and the robot should analyze the task visually, come up with a plan based on the features that it extracts, and execute similar actions to that what human did. But there will be failures regardless of how much you tune your learning algorithm or you do control tricks, etc. Even though we show only the successful cases here, there were a lot of failing experiments. Even in these simple tasks where we were just folding an object onto another or just inserting or just insertion task. So we are aware of many reasons why this is the case. Real sensor data is noisy and incomplete. This we call inevitable failures in actions, as in this. These experiments, sometimes it misses the object to lift because it's just using one-shot vision data. So when you only execute plans based on initial observations and don't use sensor feedback, or if you just rely on your simulation plans and hope that everything will, follow accordingly, you might, hit a wall and you will experience some failures. So, touch sensing can be complementary. I missed Roberto's talk, but I'm sure he motivated using touch sensing a lot and talked about the benefits of that. So yes, it can be complementary, but it is still inferior to sophisticated human skin with millions of receptors and sensitivity to many things like pressure, vibration, texture, pain, proprioception, etc. There's still a lot to be done to improve robotic tactile sensors. For instance, some of them have low resolution when they deliver pressure information, or they have repeatability or sensitivity issues. They may not be very robust when we use them extensively, but we can still use them to some extent to support visual data for various tasks. And we've seen many different gripper designs, ranging from suction grippers to underactuated hands to fully controlled anthropomorphic human-like hands with many degrees of freedom. The more the hand design resembles the human hand, we can do more Dexterous manipulations, but it becomes very complicated to control degrees of freedom in real time. We can alternatively design task or object-specific hands and fingers, but then we lose generality. So there's a trade-off. Another interesting question is to come up with an approach that is maybe hand-agnostic. So there are various sources of uncertainty inherent in this whole process, stemming from agent, environment, object, contact, and action. There will be lack of data, and there will be some modeling errors, so we should be aware of these to design robust systems and deal with inevitable failures. So perception and grasping are the first steps to do some manipulation, right? After choosing an applicable task-relevant grasp, the hand placement may not be as good as planned, as we've seen in some examples, perhaps due to calibration errors or pose estimation errors, so we should monitor the status and react accordingly. When we look at these studies, analyzing how humans deal with these issues, we see that humans make use of different sensory modalities in a causal fashion. They use vision to plan an action, to place our hand roughly, and we rely on touch sensing, and acquired signals are continuously compared with predicted ones, and this way we detect unexpected events and trigger some recovery procedures. We would like to do the same with the robots. So we look at different, let's see if this is wrong. Problems in these steps, and we try to make use of both vision and touch together in a complementary fashion and focus on data efficiency because data is expensive to acquire, especially from real robots. And we want to use probabilistic approaches to deal with uncertainty. I'll mention a few works that we did, combining vision and touch sensing for this type of tasks. We'll start with some perception problem. We'll model an unknown object shape based on building a continuous surface representation for the underlying shape. Imagine you are given a partial view like this, and the robot can go and touch the unseen areas to collect tactile measurements so that we combine vision and tactile measurements and fit a continuous surface that goes through all the measurements and resembles the real underlying shape. We can formulate this as a regression problem and fit an implicit surface, and the function we estimate maps 0 on the observation points to map and to encode an implicit function. And Gaussian processes is a good choice for this because they give us a principled way to model uncertainty about our predictions. Let me see, I can't see my phone. So for example, when we look at here, once we are around the observed data points, our model are quite confident. When we go away from the observed data points, then our model loses confidence and reflecting high uncertainty, and we can make use of this feature to explore unknown objects efficiently. And that's what we do. We can maximize the information gain by touching most uncertain areas. Uncertainty here is given by the variance from the GP estimate. Here, red color corresponds to most uncertain areas, and we acquire observations there. So we go and touch there, and then the shape resembles more to the true shape. Here we can see some more exploration examples, how the initial surface evolves as we go around and touch the most uncertain areas to maximize the information gain. And the object also is becoming similar and similar in terms of shape to the true underlying shape. And as you see that we are applying some discrete touches here, and then sometimes the object moves, so there needs to be some localization as well. Yeah, this approach works quite well with noisy data, and you can also make it a bit more computationally efficient if you use a sparse formulation without losing accuracy. In those experiments, we've done some discrete touches. Alternatively, we could also do some sliding touches, some continuous touches to increase the amount of data that we acquire in each exploration stage. We can simply follow a tactile salvage approach here by minimizing the distances between the current and the reference tactile features. Here, we can use contact centers and areas as simple features and do a quick starving approach here. And we can also apply some local finger adaptation to increase the contact area during sliding at each time frame to increase the coverage area of the area that we touch. We can push this approach in terms of increasing accuracy. With slight changes, we can even recover shapes like this in terms of holes or irregularities. And the simple trick we can apply for this is just partition the data, fit local GP models, then merge them based on their uncertainty levels, and we can capture a little bit more detailed structure from a little bit more irregular shaped objects. Given any sort of input, we need to come up with a grasping approach, decide about the configuration, and also compare them to decide which one is better, and there's many different approaches to this. A good approach is not necessarily a one-shot approach, but it can also be iterative. So when we are faced with the task of grasping an unknown object, we can follow an exploration approach, where we both explore the shape of the object at the same time, looking for better grasping configurations. So as we get a better understanding of the object shape, we can also find better grasping configurations. So a way of exploration and exploitation approach. And we aim to achieve this efficiently without an exhaustive exploration. So in this scenario, sequential decision-making tools such as Bayesian optimization would be an excellent solution because it's used for optimizing functions that are either unknown or expensive to evaluate. It maintains a statistical model, surrogate model based on the observations that we have, and it uses an acquisition function to decide where to explore next. And this acquisition function keeps a good balance between exploration and exploitation. And in our grasping context, what we will be doing is to maintain a GP where we map grasp configurations to grasp quality, and the grasp quality will be calculated based on some probabilistic measure. Because it's better to keep things probabilistic rather than relying on point estimates because things will be noisy and uncertain. So we start out with an initial GPIS model based on usual measurements, and then we enter this Bayesian optimization loop and iterate, updating our GPIS, things about the objects such as the central mass, contact points, but we always keep a probabilistic version of those. And then we iterate over these, gather observation points, gather the corresponding probabilistic quality, and keep updating our surrogate model, and keep querying based on the updated models until we find a bunch of good grasps. So we are thinking in terms of mapping between the finger configurations and the grasp quality, and our evaluation includes a probabilistic estimate of the grasp quality given the observations. And at the same time, we try to favor configurations where the fingers are directed to the object surface. And as you see here, during the exploration, the probabilistic measure increases. So we start with an initial not so good grasp, and then as we explore the object, its shape, we come up with better grasping configurations. Here are some simulation experiments. We see how the grasps evolve, how the uncertainty around the object shape changes on different objects. As you see, grasp quality increases upon a certain point, and then the grasps that find are stable enough they can withstand different type of manipulation tests such as shaking. But these are simulation experiments. We are trying to test this on real robot by also adding simultaneous localization and on top of this grasp refinement. Okay, so no matter how you do it, you come up with a grasp, and it's always a good idea to assess its final stability before we further manipulate it. This we can do using tactile data, either by approximating some analytical measures or simply just through learning, because we can see that we get different tactile signatures from good and bad grasps, so we can learn the difference. And we can further disaggregate these by adding some vision information in the form of where we are grasping the object from, as sometimes tactile readings can be similar from different parts of the object. And we can just simply pose this as a classification problem, given some tactile and visual features. When deciding which grasp to use, we also need to consider the manipulation we would like to achieve, so the task is also an important parameter. And as you see in this example, different tasks will have different requirements in terms of what type of objects we can use, stability levels, and geometric constraints. Some example tasks are here. And we can model all these sensor data. We can model the joint distribution of all these sensor data, again using a probabilistic approach, simply by using Bayesian networks. And this way, once the model is trained, we can perform inference tasks such as given a task and an object, infer the hand pose, a good hand pose. And here we see an example adaptation scenario, if the video runs. Given the task of pouring from a bottle, the grasps are evaluated based on a pre-trained network using visual data, and once the good grasp is found, then the grasp executed. And once we acquire tactile observations, we can query the same network this time also adding the tactile features, and have a better, more confident estimate. And the scenario, there is very little tactile contact, so the network predicts that it's going to fail, and it's predicted it fails during rotation, not lifting. So it's able to do this task-oriented assessment. So here we see what the network has done. For instance, in this case, to grasp the bottle, it learned that grasping from these sides is better, not from the top. Okay, so it's not just enough to lift an object and you're done, right? You should be constantly monitoring the status of what's going on. So you should be maintaining stability. And for this, once the grasp is estimated to be unstable, we can trigger some exploration and adaptation strategy. If the configuration is similar to what was experienced before, grasp stiffness can be adapted. If we learn a model based on stiffness and fingertip configuration and tactile readings. If not, if there is no resemblance, then we can trigger a local exploration approach where we move the fingers around to come up with a similar configuration. Here in this particular video, we did not use any geometric features, but there was an extension of it that made use of the object features, some geometric features to make the local exploration a bit better. Okay, I'll finish very quickly. So just a few more things to quickly just touch upon. I wanted to promote use of GPUs in robotics a little bit more. So here I will very briefly say what we did. We can simply just use model the distribution of feasible trajectories as functions that map time to robot states. So for this we can use GPs. And we can, this way, provide smooth trajectories with obstacle avoidance using uncertainty to provide better clearance away from the obstacles. I'm not going into the details of this, let me just show you how it moves around the obstacle, trying to stay away from the obstacles as much as possible. And we have some comparative analysis with similar approaches talking about benefits in the paper. Yeah, also super important to test things on a real robot and compare different methods under the same conditions. So I very much appreciate the efforts in terms of benchmarking from the community. We also have a benchmarking paper that we came up with in terms of grasping. So we have a protocol for evaluating different grasping algorithms, describing in detail how to set up the workspace, object choices, placements, how to do the grasp execution, and how to evaluate the grasp. So for instance here, we have different grasp stability levels. Some of them withstand rotation, some can even withstand these shaking movements. Okay, so these are all I want to say for today. So it's very important to use multi-sensory data. We should be able to deal with uncertainty. Probabilistic approaches seem to be quite beneficial for this. And we need to monitor the status, and once the failures are detected, we should trigger some recovery procedures and test different approaches under the same conditions. Thanks so much.
Can I ask a question about your work in object shape completion? So you're basically saying here's an algorithm how we complete the shape, and then we can grasp it more reliably. But that implies that the partial view is just not good enough. So
that's an assumption,
yes.
Oftentimes, but yeah, there are ways you can deal with it. You can move around.
Yeah, but I want to ask, why do you think that's the case? Why do you think we can't just have one single partial view?
Perhaps the back side is super irregularly shaped. Who knows? But this is, I mean, it's not just about the partial view. It's also about maybe, oftentimes, even you have a good view of the font, it is still, where is that figure? It is still going to be quite noisy and incomplete, as you see here. So oftentimes grasp planning algorithms rely on really precise contact points, etc. You know, keeping things probabilistic.
But isn't that the problem then of the algorithm that we use? Because like from physics sense, like I don't see the back of the screen of your laptop, but like just from this view, I know how to pick it up.
Yeah, again, you're doing this the human way. You assume that you can just roughly place your hand around it, and then you rely on your touch sensing. You feel it with your skin, based on the deformations, etc. So you're inherently using some other cues there. And in order to complement that and make up for it, we just closing this up with methods. I don't know if that addresses.
Okay.